Great. Yeah, so welcome everyone back to the first discussion section. So here we can discuss basically all your questions you might have had during the talks that there wasn't enough time to discuss. So it's on populations and dynamics in galactic nuclei. So those of you who send me slides, maybe go through them and start just an open discussion. So please speak up, and it's very important that everyone can basically.
Is your mic on?
Is it on?
Oh, yes.
Okay.
You just need to hold it close.
Yeah. So the first topic was suggested by Hagai. It seems to be quite extensive.
Yeah, sure.
So I just give you a minute.
Yeah, okay. So actually I have various different things I sort of mentioning or ideas that I want to put out there. Yeah, I'm not sure I need the data. Actually, maybe I'll begin with something which is not on the board there. The one interesting thing is I was thinking about the ideas of binaries around a massive central object since early in my PhD, and I was thinking actually about two different scales. One, you can think about the massive black hole and binaries around it, but you can also think about the sun and binaries around that, like binary hyperbolic objects, binary asteroids, even the Earth-Moon system. In all of those systems, you have effectively a kind of a triple system, and you could actually have some kind of a disk, which could be either gaseous or perturbative by other objects. So what I'm saying is that we can always learn from that scale and coming back to the massive black hole and vice versa. Hey, why do I mention it? Because I would like to mention two things that were not discussed so much, I think, in the literature until now. It might be interesting. One is soft binaries. Interesting thing is that we know that binaries around the massive black hole get softened with time because of binaries interactions, and usually we don't care about soft binaries. But I think that soft binaries, because they are so wide, perturbation can actually excite them to high eccentricity much easier than you excite much harder binaries. So in principle, you can actually make wide binaries into ultra-compact binaries by sending them into highly eccentric orbits. So you start with a very wide binary, it gets clicks, it randomly evolves. It's like the lost-count problem about single stars around a massive black hole, and you can get tidal disruption events. So you can think about the binary, and then it kicks by other stars and become very eccentric, and then you can actually be captured through gravitational wave capture or tidal capture if it's a main sequence star. So we might actually should be caring about soft binaries in that context. The other thing about soft binaries is because they're much wider, when you do have secular evolution, like you have in Kozai case, when they're very wide, the orbital period could be actually comparable to the timescale around the massive black hole in some cases, and you have a very strange evolution, which is not a secular evolution. Something that me and Fabi were talking about in our original paper, but there we haven't discussed so much soft binaries. But in principle, soft binaries that are very wide could be actually much more susceptible to these kinds of evolution. Why is it interesting? Because usually in Kozai evolution, you're limited by how eccentric can you be. You can be very eccentric, but you're still limited. In this quasi-secular regime, you're not necessarily limited. You can actually go through a chaotic evolution, and you can get as eccentric as you want. So for gravitational wave sources, this could also be very important. And since many of the binaries that we have in the Galactic Center would go through a soft binary phase, might actually make them, at least for a short time, very susceptible to these capture scenarios. So that was a bit about soft binaries and very wide binaries. It's not something I should mention. And feel free to stop me. I mean, I can blabber all the time. The other interesting thing is something I mentioned to some people over the break. You could have AGN disks in nuclear clusters without massive black holes. When you have an inflow of a gas cloud into the center, you still have a central potential, you have angular momentum, you should form some kind of a disk. Then you have a disk of gas, but you don't have the massive black hole. So the velocities are much lower, but you still have all the other things which are really interesting about the AGN disk. And I don't think this was actually explored. We have explored it in globular clusters when we think about formation of second generation stars. So we discussed the formation of stellar disk, second generation stellar disk, but I think in nuclear clusters it could be much more interesting. And you could have many multiple epochs of this formation of disk in this scenario. And these would be, I think, even more helpful for binary mergers. Because of the low velocities, binaries would not necessarily be as soft You can actually get binaries with much larger separation. Anyway, it's certainly going to be interesting and different, I think, from the case where you have a massive black hole. Other thing is, I would like to mention maybe the problem of the origin of binaries. In general, we need binaries to be there somehow. So they can either form in an AGN disk, so in situ formation, or they can be captured from the kind of field population around the massive black hole. But each one of these directions could have a problem. If you talk about in situ form binaries, then it means that you have star formation, which means your AGN disk is not stable anymore. So, yes.
Let me debate that point.
Okay.
So if you bring single objects into the AGN disk, and circularize their orbits, the gas will then allow them to be captured. So you can actually start with a population of single objects from your nuclear star cluster and put them in a situation which it's a single spar. It's very easy for them to match up and find binary companions because you can drain angular momentum to the gas so quickly.
Okay, so actually I want to talk first about the problems, then about the solutions. But this is one of the possible solutions, though it's not necessarily that easy. And again, I can take you to the Kuiper-belt objects in our solar system. People discuss the formation of Kuiper-belt binaries using dynamical friction. Okay, so they had in this case it had planetesimal, doesn't matter. Here you have gas, and they show how you can have two ways of forming it. Either two planetesimals coming by, and you have dynamical friction, so they dissipate some energy, they being captured into a very wide orbit, effectively really on the edge of stability. But then you can have continuous dynamical friction, and they evolve into short period binaries. This is one way. The other thing is you could actually have a three-body dynamics. So you have another three objects coming together, but you also have the dynamical friction at the same time. So again, you can actually form these, it's called the L2 and L3 mechanism for formation of Kuiper-belt binaries. So in principle, you might actually do it in an AGN disk. No one actually has studied that, I think, as far as I know. Maybe I don't know.
Secunda. Oh, Secunda, yeah.
Yeah,
Yes.
Amy, do you want to say something?
What, in terms of?
The possibility of capturing binaries in an AGN disk?
Well, I mean, I guess we just believe that, right? It's kind of like, but more. Yep,
Well,
thank you.
it's not just
It's
a
not
belief,
belief.
right?
Well, right. Okay, so it's as Mordecai said, right? If you have these black holes coming into the disk as singletons, right? The rate at which they come in is slower than the rate at which, if they were to form binaries, right? Then these binaries merge on timescales that are shorter than a
But
third.
they form.
What?
form.
Yeah, no, they form. Yeah. Well, okay, yeah. I mean, because if you can.
Nobody else knows this, Amy.
Okay.
People who read your archive.
Yes.
Okay, thank you. Yeah. Okay, so right.
Evidence. Are you making this assertion?
Right. So we have a paper that's under review right now, right? But it's up on the archive that says if you take disk torques from protoplanetary disks, right, and apply them to an AGN disk, you can essentially take these black holes that are isolated in an AGN disk, right, and they will migrate because of these torques towards an area in the disk where you have positive and negative torques canceling each other out. So essentially all the black holes are coming towards the same radius surrounding the supermassive black hole, and because they're all going the same place, they will find each other and form binaries.
And we do this.
Yeah.
And to just add to that, Amy has put this into an n-body code, and that's what happens. Like, we don't make it happen, it just happens. They form hard binaries.
And these are migration traps? Is that the word?
Right, migration traps is the word used, yeah.
Okay.
So do they form three-body or?
Well, so most often two-body, we essentially just capture up to the point of binary formation because, as we've already discussed, the physics of once they're binaries and they have, is pretty complicated. So with our n-body code, we don't really resolve that. But the idea is, like I was saying, is that the merger timescale theoretically for these black holes is rapid enough that probably you wouldn't get tertiary encounters that would be able to ionize the binaries, if that makes sense. They're hard binaries, so they definitely form a bound system.
I can answer it. That's actually the core accretion model to make planets, right?
Yes.
And yeah, I mean, like it's the method. I mean, the main route to make planets that we've been using since the 90s. So the difference between that and the Kuiper belt.
On the subject.
Oh, sorry?
Cite your paper on the subject.
Ah, sure. Well, I mean, like it isn't only my paper. Yeah. So Amy is working on an update. Sorry.
The core accretion model.
Yeah. So the core accretion is Polak et al. 94. We did. Sure. Yeah. I was going to get to it. So Amy is working on a model that is basically the application to AGN of Horn et al. 2012, which is an article that we wrote for protoplanetary disks, right? And the difference between that and Kuiper belt is the mass of the objects, right? For Kuiper belt objects, like Pluto, the mass ratio compared to the sun, that's 10 to the minus 8, right? For Earth mass planets, where then the mass ratio that would be 10 to the minus 6. So that's much easier, right, to capture them. In the Kuiper belt, you are in the stage where you can merge them, or barely so, within the lifetime of the disk. But when it comes to Earth mass planets, it's much easier. So Amy is using that model then to explain that in AGN disk. But the physics is pretty much the same. And honestly, I mean, it has to be right? Otherwise, we wouldn't have planets unless there is a big gap on our understanding of core accretion. And the reason why you mostly have binaries, right? I mean, like you don't have three bodies, because like it's much less likely that you are going to have three bodies getting together, right? I mean, like it's mostly binary accretions that would happen in the disk.
Well, I guess you have a gas dynamic of a gas drag. There are some differences, of course, but so that would be interesting. I haven't read the paper yet.
It's all right.
So
This is the point of the conference.
Certainly. So that's one way of thinking that is you can actually have, I guess, so it's a binary encounters with gas dynamic friction. This is what you have in your body, I guess.
It's more than gas dynamical friction. It's also migration. Sorry.
Yeah, you're getting a lot of exercise, Nancy, sorry.
It's also migration, bringing things into common orbits. So that's torques being from both co-orbital and Lindblad resonances that are pushing planets around, in addition to the wakes that you're thinking of as dynamical friction, which more act to circularize and reduce inclination.
The other possibilities we should consider is one is tidal capture. This is not for black hole, but the black hole or neutron star and other main signal stars. And that's specifically interesting because we could actually also have multiple generation of stars in these environments. You could even have, for example, a black hole spiraling into a very massive O star. So you can think about interesting aspects where you have a gravitational wave signature from black hole inside the envelope of a star as it inspires in. Probably most to the LISA, not to the LIGO, because I guess at the last stages you have the frequencies, the relevant frequencies wouldn't be inspiring so much. But in principle, these are some of the other interesting aspects. You have tidal capture formation of binaries. And the last thing is that something I talked with Carl, but he kind of took out all the dynamical formation of binaries, but in the disk, because he was discussing these high velocity Copernican velocities, but inside this disk, of AGN disk or stellar disk, the velocity dispersion is very small. So it's comparable to clusters or global clusters. So in principle, the same kind of mechanism of three-body formation of binaries could also work, even without any migration traps or whatever, just from basic dynamics. Anyway, so we need to think about the formation of these binaries, because if we talk about capture, binaries coming from the outside are not necessarily easy to actually get all the way through to the inner part of the AGN disk, because by the time they get there, most of them merge or soften or whatever from other reasons. For example, the paper that Fabio mentioned, Zhang et al., they try to do calculation. If you actually look on the paper, you see that in the central point 1 particle, so you already don't have any binaries left, because they come from the outside and then slowly soften and being destroyed. So it might not be that easy to capture all of them through this kind of mechanism. On the other hand, you can actually capture them from very far away. So people discussed this already in the early 2000s, or 2005, I think. So we have a binary, or people discuss single stars. You can have a star coming from very far, parsecs away, coming through the AGN disk, dissipating, and then coming over and over again, like the way that you capture stars in the field, but not from the close by inner region, but from the outside. So in principle, you can actually capture binaries from the outside into the disk in the same manner. So you can have this outside capture of binaries. Anyway, what I'm saying is that we should think about all the binary formation mechanism, how to actually put them in. It's not necessarily trivial. And so one of them is already out there. We should actually maybe calculate all the rest and see what kind of binaries can we form in this case. So that's a bit about the dynamics. I have other aspects, but maybe other people want to talk. I mean, I've already talked a lot, probably for more than one slide.
Don't have so many topics.
So, I mean, one thing I just want to jump off of based on that, with three-body formation, right, if you have three things coming in, you mostly expect the binaries you form to have a thermal eccentricity distribution, so your mean eccentricity is going to be, or mean eccentricity is going to be 0.67. For the case where you have like gas drag creating binaries out of two bodies, what eccentricity distribution do you expect out of that? It's not going to be, I would imagine it's not thermal, but I have no idea. Do you?
Yeah, I don't think I have an answer to that, because like I said,
If you're projecting well enough, I can.
Well, but
so that-
for
yeah.
record,
Oh, for recording,
no.
yeah, you're right, yeah.
yeah. Go ahead.
Actually, hang on, there was this.
Andre was
Oh.
also-
Oh, since you were saying something related to what Amy
Yeah.
was saying.
Yeah. Okay. Yeah.
I have
Yeah.
a similar question.
This
But
is
it's
an
not about-
experiment, folks, let's see if it works.
I just had a similar question.
Yeah.
Do you have different mass particles in your simulation? So is there a preference for mass ratio? Of
Yeah.
matters?
That's a good question. Yeah. So we have different mass distributions, whether fiducial or based on like a group IMF. But I don't think there's necessarily a preference for mass ratio. At least we haven't looked into that specifically. But the idea is that, right, if you're more massive, you're going to migrate faster. So the more massive ones tend to. I guess with the migration rates that we're using with the, so I, in that way, right, the more massive ones.
Like for the same type of migration.
Right, sure, yes, sorry, yeah, right. Right, because, our mass range is about 5 solar masses up to, after, initially 30 is the most massive, but after they merge, we build ones up to about 100 solar masses, but that's the maximum.
I mean, the reason I like this idea is that if you have different ways of forming these binaries and they have different eccentricity distributions, then when they get inside the gas disk, it's like what Andrew was showing us earlier, you get weird torques depending on the eccentricity, so you might have different evolutionary pathways, and they might even take longer to transit from like LISA to LIGO. Like there'd be
Accretion might also prefer a certain eccentricity. We still don't know the answer to that from these simulations. I was just saying, circumbinary accretion could also drive the binary to a preferred eccentricity, but we don't know the answer to that question yet.
Yeah. So So there's been some preliminary work on that that's not published yet, but first of all, there's a lump in the disk which tends to the cavity itself is eccentric, so that can drive eccentricity into the binary. When we've done a live binary, it's very tricky to do, but the preliminary results show that it drives eccentricity until the secondary starts slamming into the cavity wall, which puts a cap on the eccentricity. But I can't quote a number yet because I'm not certain. Similar things happen when you have a planet and a gap in a protoplanetary disk, that you can excite eccentricity until the planet starts hitting the gap wall.
So hang on, I'd like to ask Andrew a question. Okay, well, sure. So offline, we were talking about the fact that even very small objects can open gaps. It's very small binaries can actually open cavities. So I was wondering how effective, do those start growing eccentricity before they open a cavity, and does that actually then extend beyond what you might get? Because even if you have a small cavity, you might already be very eccentric. So just while you're still embedded in the disk, are you already growing eccentricity?
Yeah, sorry. For that particular study, we used a fixed circular orbit. That's already challenging to do because you need thousands of orbits. It's actually interesting, you start by growing 2 gaps, and then they eventually hollow out their center. So that would be an extremely challenging thing to try to do with a live binary in the future. But first we need to really understand the details of torques and on the fixed binary case.
But the expectation was earlier, in earlier papers, was that if there's no gap, then the eccentricity will generally decrease, right?
Yeah.
But if there's a gap, then it would increase. So before you actually open a gap, it would probably decrease the eccentricity.
Yeah. I'm just not sure about the double gap phase. I'm not sure what would happen there, actually. That's an interesting thing to look at.
All right, so maybe we can postpone to the next session your next comments, because they're usually for future work. So we can just move on.
What do you need?
Oh,
you have use the mouse here.
It's okay.
Want to go forward?
Okay, so I don't know, are you still there, Nate?
Yep.
Nate?
Yep, I am.
So yeah, so I put up the slide that you've sent me, if you want to explain what it was on.
Let's see.
Sure.
Hang on.
I'm just going to turn down my volume so I can't hear my obnoxious voice. And then I'll put it back up so I can take questions or whatever afterwards. So I think, so based on work initially started by J.J. Monahan, Maury Valtonen, and others, and most recently sort of revisited by Nick Stone and myself, we have a pretty decent understanding of what to expect for the outcomes of binary single interactions, or if you prefer, triple disruptions. And the work that I'm going to talk about or advertise is preliminary work that sort of addresses how the isolated case changes if you put the 3-body system deep in a Keplerian potential. And so this is work being led by Alessandro Trani, Mario Spera, and Michiko Fuji. And they've been using a code developed by Alessandro and Mario called Tsunami, which incorporates the AR chain integrator designed to do extreme mass ratios and very high eccentricities with great accuracy. And so what I'm showing here is a comparison of what you get out for the 3-body disruption by varying the position of the 3-body system within a Keplerian potential. So the basic setup is you have an SMBH at the center, and you've got some triple system that you start at various radii, various distances from the SMBH. And these are shown by the different colors. And we compare these to the isolated case, which is shown by the black lines. And we look at 2 different extremes defined by this dimensionless angular momentum parameter. And so the low angular momentum case, W equals 0, you can think of as starting the triple out in a retrograde configuration. So the inner binary starts with a semi-major axis of 1 AU, and it's got an outer triple companion orbiting at about 2 AU. And so this does not meet the criterion for a stable triple system. And so it naturally disrupts, ejecting one star and leaving behind a binary. And in the other extreme, you have the high angular momentum case, which is effectively the same thing, 1 AU and 2 AU, but starting it out in the prograde configuration. So again, left is retrograde, right is prograde. And what we find is that, so if you've got the triple system orbiting about an SMBH, you're introducing an additional Coriolis force as well as a tidal force that's going to ultimately change the physics of the disruption process. And so we see that if you start the triple system pretty far out from the SMBH, then what you get out looks very similar to the isolated case. But as you start to move the triple system deeper and deeper into the Keplerian potential, you start to deviate away from this isolated case. And so I should mention this is pretty preliminary work. It should be out soon, but we've not, it's an interpretation of these results at this point. So perhaps take it with a grain of salt and feel free to challenge. But the basic idea here is that if you start by thinking about how breakup has to happen in isolation, you somehow need to have all 3 stars end up in a sufficiently small volume to accelerate one star to ejection. And so this translates into lower angular momentum interactions, tending toward being more compact. So the surviving binary ends up being more compact, more eccentric, and you get higher ejection velocities for the escaping single star relative to higher angular momentum interactions. Okay, so now if you then increase the Coriolis force and of course the tidal force, this lowers the threshold for escape. And so you naively expect it to somewhat undo the above effects. And I think this is more or less what we're seeing in the plots I show here. So the tendency for the eccentricity distribution, for example, to reapproach thermal in the low angular momentum case when the Coriolis force is large. So the basic idea, so if you think about the higher angular momentum limit, there's this tendency to produce more compact binaries when the 3-body system is deeper in the Keplerian potential. So when there's a stronger Coriolis force. And again, I think this is because it lowers the threshold for escape. So the single star is able to escape farther away from the binary center of mass than it could in the isolated case. And therefore, the escaping single star is able to take away more angular momentum, leaving behind a more compact binary. And it's kind of hard to pull apart if you think it's the Coriolis force or the tidal field that's doing the above, but naively, I would expect them both to contribute to lowering the threshold for escape, since the Coriolis force adds an outward acceleration in the radial direction, whereas the differential force of gravity effectively just assists to pull apart the triple star system. And so I guess the main things to point out here is that the main effects in the low angular momentum limit, you see the eccentricity, you see in isolation, there's this tendency to produce a suprathermal eccentricity distribution. And as you go deeper into the Keplerian potential, it starts to reapproach thermal. And then if you look at the high angular momentum case, again, you mostly see the effects in the semi-major axis of the leftover binary, and you're basically able to produce more compact binaries than you could in the isolated case. And so I think these are very nice results done by Alessandro, Mario, Michiko, and myself, because they start to address the question, for example, the setup is basically very similar to what I think you'd expect if you have a binary that starts in the migration trap of an AGN disk, and another star starts to drift inwards, and it either hits the binary on either a retrograde or prograde orbit. And so you can compare to these plots and look at where the migration trap is relative to the SMBH, get a sense of how strong the Coriolis force is, and then you can start to ask yourself, how would the outcomes of the interaction differ from the isolated case? And communication, I'll put my volume back up.
Thanks, Nate.
Okay.
Any comments or questions to Nate?
Hi, Nathan.
Hey.
So I think we actually discussed it ourselves. I think at some point I sent you this paper or draft of these students I had. So effectively what you get is that you lower the escape velocity that you need in principle, right?
I think so.
Okay, so in principle you can do all the statistical study of this thing and just instead of using the escape velocity, use a limited escape velocity, and then you get a smaller number of of repeating encounters in a sense. And this so that explains the whole statistics in principle, this kind of idea. Just wanted to clarify.
Yeah, I think so. But I think, I mean, bringing in some of the work you've been doing on the shape of the Hill sphere, right? The Hill sphere is not spherically symmetric. So yeah, I think it does. So if you want to try to come up with some sort of analytic description of this, which I myself have not yet tried, I think that's the way you'd go. You'd look at the escape velocity as a function of the shape of your Hill sphere. And basically, yeah, it probably I think it lowers the threshold for escape, so you're able to escape at lower velocity.
Okay, I can mention something that you're working on. So when you have a binary sinking encounter, right? You have the star coming out, and then one of the stars is coming out for far distance and coming back, and this could happen for tens of times. And each time you have a probability of getting one of them to escape. So obviously you'd have a parallel distribution of how many times they're going through this case. Each time they survive, they have another time. As it turns out, if you actually look on the n-by simulations, these are uncorrelated. Each encounter is uncorrelated with the next one. So in principle, you could actually do, and this is something we did, we haven't published yet, you can actually do a statistical analysis of what, for example, should be the expected distribution of how many encounters you should have. And each time you actually exchange energy, so you have the effective final energy of the binary. So you can actually get this hardening from these kinds of calculation. The nice thing about this kind of statistical analysis is here we assume that probability that you're getting to escape depends on the escape velocity that you have. So in principle, if you now want to include any kind of environment, like Nathan suggests, either a cluster environment where you have the density of the cluster because of other stars, or a massive black hole, or the sun and Kuiper belt binaries, you can just lower the escape velocity, but you can use exactly the same statistical method, and you should, in principle, immediately get these results for this new case. The other interesting thing about it is because these kicks are uncorrelated, and they only depend on, in what Nathan suggested, for example, this dimensionless angular parameter, so you can actually include dissipative effects. Let's say you have a tidal interaction during the encounter. You dissipate the energy, so now you have a lower energy, but you have another binary sinking encounter just with a new lower energy. So you can, again, use the same statistical analysis. Now you do have a correlation, because if you have a dissipative interaction, the next one would be with lower energy. But this is something now you can use this kind of, I don't know, let's say Markov chain statistics. Each encounter depends on the previous one, and you can again get this overall statistics. So I think at least there's such a chance of actually getting this problem, doing it analytically, or I mean in a statistical manner, but more or less analytically. Anyway, it would be an interesting thing that Nathan, we should certainly discuss it.
Right, so if I could just comment really, so actually, like if you take Grisham et al. 2018, and if you're in a very thin AGN disk, then you're restricted to coplanar interactions. And I think it actually becomes relatively straightforward, since you can just look at the Hill radius on either side of the binary using Grisham et al., and then use this to address basically the probability of escape and how you'd expect that to change. So that particular limit could be quite simple and immediately tractable. The other thing I'd say, so I have heard people talking about how gas dissipation affects the outcomes of these three-body interactions. And I think the guy is ultimately right, but I think you can qualitatively try to get like an understanding of what you'd expect just by thinking about two limits. So you can go to very negative energies and low angular momentum, where here I think the effects of gas dampening would be a lot less severe, since the average velocities are pretty high. So gas damping isn't going to be all that effective, and really the only thing that probably matters is the fact that you've got gas in there, so that's deepening your potential, and probably truncating low escape velocities and pushing your distribution of escape velocities toward higher velocities. And then in the other limit, where you've got a total energy close to zero, and high angular momentum, I think this is probably where the gas damping really starts to matter. And the reason is just because when you have a wide binary or low total energies and high angular momentum, the interaction times tend to be longer. It's harder to eject a single star since the probability that all 3 stars will end up in a small enough volume to accelerate one star to escape is low. And so gas damping will have enough time to actually deplete angular momentum and energy and start pushing you towards different distributions for the outcomes. But I think it's definitely a problem worth looking into more.
All right, thanks, Nate. I think we're running out of time for this topic, but I just wanted to ask very quickly if your distributions that you're showing, do these have direct consequences for LIGO sources? So would these sources be distinguishable in terms of LIGO, these types of eccentricities or semi-major axes by the time it grinds down to the LIGO band? I assume no, but...
Yeah, I think that's a good question. I think the answer is ultimately yes. And I think the way that we can start to tackle that is probably going to be when we have a lot of measurements. And so we can actually start looking at statistics and things like this. And yeah, it definitely needs to think about how exactly this can either help us understand the astrophysical environments from which these mergers are coming from, or even confound our understanding of them. It's a little more complicated.
All right, great, thanks, Nate. So let's move on to the next topic. Actually, I was about to suggest this. So this is about, just to advertise our work on black hole disks. So this is a work done by a student at Ötvös Ákos Szörgyén. So we basically ran a Monte Carlo simulation of the dynamical interaction of objects in galactic nuclei. And what we find is what was actually already predicted by Roch and Tremaine in '96, that higher mass objects tend to be segregating in a disk if you start from an anisotropic distribution. So if you start from a completely isotropic distribution of orbits, then you retain that. So then all the objects will have an isotropic distribution. But if you initially have an anisotropic distribution, for example, if you merge together gas clumps to form the star cluster, or you merge globular clusters to build up the nuclear star cluster, in that case, the heavier objects tend to have an angular momentum vector direction distribution that is clumped up here. So the high mass objects have an angular momentum vector direction pointing in the same way, whereas low mass objects are isotropically distributed in angular momentum. So this is really interesting because it suggests that black holes are not completely isotropically distributed in galactic centers, just because of dynamical effects, even without gas.
Is this the steady state distribution, like the distribution?
This is the steady state distribution, yes.
And how does it pick? Is it the galactic plane that picks, right? How does it pick its preferred plane?
So there's an overall angular momentum of the system.
Oh, it
just
is, yeah,
by the initial condition, and that sets the direction. But the really interesting new thing, which is not published yet, but I just want to show really quickly here, it's going to be published in a week or so, is that even in globular, this happens even in globular clusters. So if you just put in, so we start from a rotating initial condition of a King model with a mass distribution, and at different radii we measure this enhancement factor, basically the average mass in a spherical shell. This is denoted by m average r. So this is the average mass in a spherical shell at a particular radius, and then compare the average mass of orbits with different inclinations. And what we find is that that orbits which have an inclination in the plane of the angular momentum of the cluster have on average higher mass. So the average star has a higher mass in that plane compared to stars in other orbital inclinations. So this just shows that basically a disk forms.
So what's really interesting about this is that for low mass gas inflow, these black hole disks could bias the plane of the inflow, right? Their mass will tend to dominate, and so you might expect a correlation between these black hole disks and the flow of low luminosity systems where there isn't that much mass inflowing. So that would be an interesting thing to test.
I agree. So the gas and the direction of the gas, so the orbital plane of the gas will be oriented in the direction of this.
Well, I have an observer sitting fairly near me, and he has a flattened distribution of black holes and a gas disk. And what I don't know is, are they in a common plane? Is the gas disk around Sagittarius star in the same plane as your stellar black hole distribution?
Gas. I don't know which gas you're talking about, but there's a spiral going to the galactic. It's not aligned with the black hole, but our black hole distribution is actually aligned with the nuclear star cluster. And again, remember we are tracking the X-ray binary distribution. So he's actually simulating the isolated black hole distribution, right? So if you convolve his distribution with a bunch of low mass star distribution in the NSC, then you may end up with the X-ray binary distribution, which is close to the NSC orientation. So that's what I was actually talking to Brian before this session. So it's really interesting for us to detect more X-ray binaries and then tell you how much alignment we get, exactly aligned with an NSC, or maybe there's a slight offset, right? So that kind of study is very interesting to Ben's study. So stay tuned. So in a year or so, we're gonna give you a better data.
Very briefly, I think in the Galactic Center, for what you were mentioning, there is the circumnuclear disk, but that's very massive compared to the black hole disk, right? It's also on a different physical scale. So, it could be that the black holes are in that plane because that's how they were fed in, but I don't know if the logic can work the other way. We can't say because the black holes are in this plane on larger scales, the gas.
So if I remember this correctly, NSC size is about 4 or 5 parsecs across the plane, and then black hole we are finding is within 1 parsec. But remember, there's a distribution, so you have more low mass stars near the center. So we really need to compare not just the orientation, but the 3-dimensional distribution of our black holes and the NSC near the core. So we just don't have enough samples to do this. But yeah, we'll do that in the future.
So since this should also apply in globular clusters, which might be a little bit easier, are there any observables that we could chase in globular clusters to validate this?
Yeah, so that's a very good question, and we're working on this. So we don't know yet, but of course, in globular clusters, all you see is the low mass stars, right? And the prediction is that low mass stars would be isotropically distributed. It's only the high mass objects, which are all black holes by now, which would be not.
What about X-ray binaries?
Or yeah. If
on XP.
It depends on how massive the object is. The more massive, the thinner the distribution would be. And even the highest mass objects, you shouldn't think of this as a very thin, like a razor thin disk. It's like a very thick torus or something.
But can I comment on the globular clusters? So unlike the Galactic Center, no one is monitoring globular clusters every day. So the only luck is if a black hole LMXP is in the globular cluster, have a big outburst, which is caught by an all-sky monitoring by a MAXI or SwiftBot. And then to do this, you need to have some close by globular clusters, and you have to have a luminosity up to 10 to 36 ergs per second, something. But like I said, black hole LMXPs have a very long recurrence time, so they rarely outburst. So bad news for you, but I don't think we can really find the black hole LMXPs from a globular clusters, unless you look at the system all the time with something like Chandra. But near the core, we have all these source confusion problems. So I don't know how crowded this is, but it's going to be very challenging. So it's a different story from the Galactic Center.
Yeah, but there could be other observables in principle. So in principle, you could consider just the velocity dispersion as a function of radius and see changes as a function of angle. And the overall evolution of the cluster could be different. For example, core collapse could occur in a different, different configuration, which may have large size effects in the end. I don't know, but we have to check this.
Does this picture include also the evolution of the black hole population due to dynamical friction, or assuming that?
It does. You mean?
You mean the black holes will segregate in the center of the star cluster?
Yes. So this is just an n-body simulation.
It is.
Yeah.
Full n-body.
Full direct
How
n-body.
many black hole stars?
It's so we experimented between 64K to 256K objects in total, and a fraction of those would be black holes. So there's a mass spectrum which is m to the -2, which we tried.
So even in the very center of the star cluster, where most of the black holes are, you still find some anisotropy or like differential.
Yeah. So at the very center of the cluster, as you see, you find a very big anisotropy for the high mass objects.
So this is for the cluster, but for the galactic center.
For the galactic center, we don't have a simulation, a full n-body simulation yet. In the galactic center, all we have is this Monte Carlo simulation at the moment.
What's the fraction of? I remember the original paper from 2011 or so. We had this discussion about it. What's the actual mass of the black hole or the massive object that you use? Because if I remember correctly, unless you used this in the galactic center stuff, more massive objects, you didn't get a very thin disk. So, okay. The other thing I should mention that if you do have a star formation in a disk, just because of regular mass segregation, you have the massive the black holes or initially the O stars, but later on the black holes, the most massive ones, and you have mass segregation, but in this case in the inclination, you have mass stratification. So even if you have regular star formation in a disk, the black holes would remain in much lower velocity dispersion for a longer time. And this signature could actually continue for even 100 megayears. We now have simulations of even multiple disks, and you can still see these signatures. So even irrespectively, you should always have, if you're forming a disk, you should have the black holes be much more compact configuration.
Yeah, next question. Oh, sorry.
That's right. Just once you form a binary, don't you start kicking out the other black holes?
That was going to be my question.
Yeah, so apparently you can retain a much larger population of black holes than previously thought. So maybe Carl can comment on this in general.
Yeah, in general, but you're still going to have a huge mass loss from the center. I mean, you're kicking out for a massive cluster on order 1,000 to 2,000. Like, it's entirely reasonable to still kick out the entire system over the time. So actually, now that I have the microphone, I had a question about the in-body simulations. How did you resolve vector resonant relaxation with an in-body simulation? Because don't you need extremely high phase precision to do that? Or?
Yeah, so we actually used a relatively large softening length, 10 to the -4, 10 to the -5. That kills some of the two-body effects, which would reduce the effect of vector resonant relaxation. But yeah, no, we just tried to use a small time step, and that's it. So you don't need to. You need a relatively large number of stars, but other than that, I don't know. Yeah. Okay.
Did you look at past simulation? I know, like Hagen's simulation, he did a full clusters, right?
Yeah.
And by the answer evolution.
Yeah. The problem is that previous simulations usually started with either isotropic configurations or isotropic and non-rotating configurations. So the prediction is if you start from isotropic non-rotating configuration, you stay isotropic and non-rotating. But if you start from either rotation or anisotropy, then you build up some kind of anisotropy for the high mass.
one of the Dragon simulations, these million body simulations, had initial rotation for it.
Yeah,
They
you
see
should,
anything like this?
you should check that. It's not easy to extract this type of information. Well, you should just run the same type of analysis for their simulations.
I couldn't fully understand. How do they lose energy to form the disk? And if that happens to black holes, should that also happen to dark matter?
They don't lose. So the question was.
Oh, sure. So how exactly do they lose energy, right? And if that happens to black holes, should that also happen to dark matter?
So they don't lose energy. So the initial potential energy is more or less conserved. This is this vector resonant relaxation energy, which is conserved. So the initial anisotropy is retained in some sense. So the energy is conserved. And if this would affect dark matter. So the dark matter, if the dark matter particles are lower mass, they should be kicked to higher mass, higher altitudes. So they should become more isotropic.
Basically what I'm asking should then expect so my question is that if that happens to black holes that are not interacting with each other through anything else, gravity, that's exactly the same thing dark matter does. So does your model also predict that dark matter would form a disk?
Only if it's collisional evolution, and dark matter on large scales is collisionless. But it's a good question for, dwarf galaxies, maybe, because vector resonant relaxation timescale is shorter than two-body relaxation timescale. In that case, maybe in the inner parts, you could form a disk. Yeah, but let's move on to Barry's.
So the point I just wanted to make here is if we put on our pessimistic hat, for whatever reason, it may be that AGN disks form binaries and make them relatively hard, but that's all that they do, right? It may be that it doesn't quite get them to merger, right? Because we're missing something, or we're overestimating torques, or whatever it is. But it could be then that the AGN disk provides a seed population of hard binaries that then feeds into the dynamics models that Carl and Fabio were talking about. So AGN could be the catalyst. Even if they fail, they could be the catalyst for dynamics, general dynamics channel. So just a general point to keep in mind if you're wearing a Mets hat.
Also kill. You can actually have a gas softening of binaries in principle. I mean, I discussed the concepts of binaries in the protoplanetary disk, and we also discussed something we call the wind shearing radius, like the heat radius, but because of wind shearing. If you have a differential acceleration of the two objects, right, it can both help you in spell, but if you actually on the outside, it can also shear you apart. So it depends. So it can also go both sides, and if
you should wear this.
and if we have this positive, if we actually get outside, then certainly we are on the worst situation we were before. So we need to think about that too.
Okay, so let's move on to the next topic by Imre.
Yeah, so just with one eye on the Wednesday session on observables. So I think one of the interesting questions is how do the black hole properties change as the individual black holes or binaries move into the disk? We did a Monte Carlo study that was put on the archive very recently. And what we find, which is, again, hopefully going to be related to observability as well, is that this alignment with the AGN disk actually prefers heavier black holes. So if we start off with any kind of expected parallel mass spectrum, this mass spectrum will actually harden by roughly an index of 1 as the black holes move into the disk. So this is something that can be easily verified with observations once we start seeing these black hole mergers, if they happen within the disk. Other things that will happen to black holes as they move in, if they for example, merge in a migration trap, then we should expect very different kinds of mass fractions than if, for example, a binary moves in, then the binary will keep its mass fraction. But if we really merge these binaries in the mass trap, migration trap, then we should essentially randomly align or randomly assign the masses. So we should have actually very low mass fractions. And another thing that's, I think, very interesting is how the alignment or how the black holes are moving into AGN disks depend on the properties of the disk itself, migration or mass rate, or even the supermassive black hole mass. What we find in this recent Monte Carlo study is that the dependence is actually very low. The reason is that black holes that are fairly well aligned with the AGN disk to start with will migrate in fairly quickly, so it doesn't really matter if it's a dense disk or not, while if we are misaligned to start with, then this migration will be very slow, so it doesn't matter again, which means essentially that if we're looking at which AGN will produce these mergers, then the dependence will not be strong. So we don't learn much by knowing the properties of the AGN disk migration rate or the supermassive black hole mass, for example. In any case, again, just looking towards observability, actually AGN are still going to be much more rare than regular galaxies, so we can use the localization from gravitational wave observations, for example, to correlate these things. So I think it's very useful to know where AGN are to start with.
You want to mention this result? Because
So I was a little confused with whether I should say that or should I save it to Wednesday, but the bottom, because that's observable, but the bottom line is.
You saw Bika's question on the first topic.
Right.
Bounce back.
Yeah.
Sorry, so maybe this is like a terminology issue, but I just want to be clear, because I'm a little bit surprised by something that you said, that the migration rate depends on you mean by the orbital inclination angle?
Yes.
Compared to the disk?
Yes. Okay,
and so then that the more massive objects are going to come into alignment more rapidly.
That's right.
And so, and you said that the mass, so I think the thing that I was expecting you to say, and I think this is what you meant, so let me just make sure that I understand, that the mass ratio, if there's a migration trap, then you would expect that the mass ratio of the merged binaries would be low because they're going to swap partners until they get to relatively equal mass binaries because there's a lot of them around. Is that basically?
No, not exactly. So basically, if you had a so basically if you have a fairly low rate of migration into the right in the middle. If you have a low rate of migration into the disk, then essentially you are going to be randomly assigning the black holes that are moving into the disk. So if you have two black holes out of the, I don't know, 20,000 that are in the galaxy center move into the disk because they happen to be aligned with the AGN disk better, then those are going to be merging. And so what masses you're selecting there will be independent essentially. So this is going to be a random assignment, exactly. So it's not related to how they interact. It's really that they are just independent. And that should be a way to differentiate between that and if a binary, for example, moves in and then something happens to it, because then there's going to be a correlation between the masses to start with. Right?
Because they are because
they're already a binary, exactly.
I understand
exactly.
what you're saying. Yes. Okay.
Right. So that's going to be a way to differentiate, which I was going to mention on Wednesday as well. So that's why it's a little hard.
I don't know that I agree, but okay, yeah.
Just wanted to mention quickly that any initial mass ratios that you might have might be erased by accretion, right? Because sometimes you find, at least in circumbinary disk accretion models, that the smaller one accretes at a much higher rate. And so if there's time and there's enough gas, so I think there's enough gas, then you might expect the mass ratio to equalize, which is also interesting, but worth further exploration.
But in this case, would it go in the opposite direction?
Sorry,
somebody. It's the primary orbiting relative to the gas with less. So in this case, wouldn't you naively expect it to go in the opposite direction because the primary is orbit velocity relative to the gas is smaller, and the secondary is whipping around the primary?
So
So it would drive it to small mass ratios if there's significant accretion.
So the primary accretes more, but what matters is how much it accretes per its own mass. So the ratio of m dot secondary to m secondary is larger than m dot primary to m primary.
But isn't the merger timescale just a mega years?
So my general explanation would be that the merger may be different. I mean, sorry, the accretion rate may be different, but the amount of accretion will be very small compared to the mass of the black hole. So I would not expect the masses to change enough that that could be observable. Okay, everything just happens very quickly, which is nice for the rate, but it's bad for these kind of effects, right? So you have order million years for everything. You will not accrete enough on that time frame, unfortunately. Unfortunately for the mass, fortunately for, again, merging many things.
So I would like to mention that maybe much more important for the mass function would be the basic segregation in the nuclear cluster. So you have this so-called strong mass segregation. In a case where you have a relatively small number of massive objects, you have something which is even stronger than regular mass segregation, and you get an extreme mass function. So we have calculation people did for us. We did more recently by my student Danora Aaron and myself, 2016, Aaron and Peretz. We showed the distribution of black holes of different masses. For example, 10 solar mass versus 30 solar mass. What you get in nuclear cluster is it's always going to be completely dominated by the most massive black holes. And dependence is even much stronger in this delta B. Okay, you can actually get, if you have 10 solar mass black holes, and even if you take a mass function of m to the -2, once you put 30 solar mass black holes, the small number of 30 solar mass black holes, they're completely dominated, and 10 solar mass black holes go down by two orders of magnitude below. So any kind of nuclear cluster mergers of black holes would be completely dominated by the mass function because of the strong mass segregation, even before the issue of the disk itself. Something that people, I think, miss in this context. Anything that comes from a galactic nuclei, you should have intrinsic strong mass segregation would strongly affect it, and that does depend strongly on the kind of massive black hole that you have. If you have low mass massive black hole, the relaxation time scale is short, and you can have this strong mass segregation. If you go to high mass black holes, relaxation time is too long, and you don't have this strong mass segregation, then you go back to this. So this is something which really discriminates in both low mass and high mass black holes, and give you an extreme mass function in terms of dependency of high mass. But it doesn't care about the mass ratio. It's just the total mass of either the binary or the single mass.
It's also the.
Well, if you're relevant to him, because I have a slightly different. Here, I'll pass back.
I was gonna comment on what just a guy said, and I mean, it is true that there is mass segregation, and the most massive black holes would be closer to the supermassive black hole. But for example, in the Lidov-Kozai merger process, so what we find is that the mass function of the black hole binary mergers is really set by the initial mass function of the stars, because mergers happen typically on timescales that are much shorter than the other relevant dynamical processes that, for example, drive the black hole population towards the supermassive black hole. So the black hole binary black hole binaries merge before they can actually segregate to the center. So in our models, we don't see any really, we don't see this preferential selection, let's say, of more massive black holes.
It depends on your source term, right? If you assume that the stars form in situ and then take short time scale, you don't care about segregation.
Right.
If they formed at larger scale, then migrated in, then you do care. So it depends on what you assume on the source term of your binaries. So that also really affects. If you have in situ formation of stars in the disk, it's one thing. If you have capture into the AGN disk, it's a different thing. In the context of both Kozai and the disk, depends on what's your source term of binary.
Yeah, I agree.
So just on this very point, where are the black holes coming from is actually pretty important. And I would make the point that under the most, I don't know if you want to say optimistic or pessimistic, under the most extreme circumstances, the period of galactic nucleus quiescence is multiple times, at least typically an order of magnitude, maybe 2 orders of magnitude, longer than the period of activity, just based on the fraction of galaxies that are currently active, right? Which at least that we can observe. And what that means is that if you have a lot of time to form stars, most of the stars are probably not going to form in the AGN disk. Most of the stars that make the black holes that we care about are not likely to form in the AGN disk. You're much more likely to form them in a quiescent period or to have them arrive. You can have episodes of star formation, starburst galaxies, and you can have migration having them arrive. And so I'm not 100% sure that that if you have stars, if you have black holes, stellar mass black holes that are sitting in the galactic nucleus, it's quiescent. The gas arrives, then the migration rate is going to be determined in part by the mass of the stellar mass black holes. And so you might still end up with pretty co-equal masses because it's not a totally random draw. And so I'm not sure that actually the mass ratio is going to be a really clean thing. And also, if you have a long period of quiescence and there's no gas damping, then you're going to have a lot of interactions which are more likely to be disruptive of a binary than hardening. And so you might end up, if you have, let's say, in your initial gas cloud, you form some stars, you have some binary fraction. The binary fraction of the stellar mass black holes, say 10 megayears later, is not likely to be as high. And maybe 100 megayears later is really not likely to be as high because you're going to have all these disruptive interactions. And so it's not even obvious to me that the binaries that you start with at the beginning of the AGN phase are going to be reflective of what happens in star formation, where I agree, you know, all other things being equal, you're going to expect pretty equal mass stellar mass black holes. So I would just be extremely cautious of using the mass ratio of the detected binaries as direct evidence. So I think there's a lot of modeling that has to go in there.
Yeah, these are very good points. So let me just add in particular that this mass hardening that we found was independent of the underlying spectrum. So if you start off with the harder spectrum, this comes on top of that essentially.
Yeah,
the hardening is independent, so it's even more. I would say, so I totally agree with you. I would say that the main competition, if you will, is field binaries. So I think what's going to be an interesting question, especially early on, is how we can differentiate between field binaries and all this other stuff. So I totally agree with you that it's very complicated to go one step further than that, just with this, for example, mass ratio or even the mass distribution. I would say that differentiating between a field binary distribution and anything like this should be easy, and everything you suggested is the next step essentially, right? So that, you know, what happens afterwards. But I can't really imagine any situation where you keep mostly what's in the field binary in this scenario. So that should be easier.
Fair.
Yeah.
Okay, so let's move on to the next topic, which is related. It's by Rainer.
Okay. Yeah. So I'm going to talk about something similar to what was just in the last slide. That image on the right, for instance, looks very similar to one on the last, but it's slightly different. So we're just looking at the effect of knowing the inclination angle of binary black holes and how this relates to studying the populations of binary black holes detectable by LIGO that are coming from or being driven by AGNs. So if we have some sort of population of stellar mass black holes, binary black hole pairs that are inside of the AGN disk have been captured or captured and aligned with the AGN disk, then we have a lot of information about the inclination angles of those binary black holes. And so we can use that in our analysis of the gravitational waves that we detect to improve our understanding of where they are coming from and get more precision on the localization volume
of the black holes themselves. And so we did a study of this with the image on the left that you can see. We generated a big population of potentially detectable binary black hole pairs, and we localized them with different levels of knowledge about their inclinations. So the curve, so it's a cumulative plot of the constrained volumes. So the curve on the very right is having no information about the inclination of these binary black holes. And so the more right you are, the higher volume you have constrained to. It's less precise in volume. And then if you know the inclination as a prior to plus or minus 30 degrees, you get a 35% decrease in your volume localization. And if you know it to plus or minus 5 or exactly, you get about a factor of 3 in improvement in volume localization. So moving on to the right side of the screen, you can use this to statistically study the AGN-driven binary black hole subpopulation. So as was on Imre's last slide, and I guess we talked about more Wednesday, but the idea would be to collect large samples of these binary black holes, count the number of AGNs associated with them, and then have different expected numbers of AGNs depending on whether the binary black hole is generated in an AGN or not, and then basically do the statistics on that and establish what fraction of those binary black holes are being generated by the AGNs. And so this plot shows after we take into account, say, we take all of those binary black holes and we improve their volume localization by a factor of 3, and we redo that analysis, then how much does it improve? And it reduces the number of detections needed by a factor of 3. So on that x-axis is the fraction of black holes that are formed by AGNs, and on the y-axis, the left y-axis, is the number of detections necessary to reach 3 sigma confidence in that respective AGN fraction. So if you want to learn more, you can see that paper at the bottom. It's on the archive right now. And yeah, let me know if you have any thoughts.
So this sounds super awesome, but how the heck do we know what the inclination angle is of the AGN disk, number one? And that already assumes, right, that we've pinpointed it to a single AGN, whereas even in this method, there's going to be probably a few in the LIGO error volume. So I suppose it would be still probably at some level helpful to say, well, it's either, NGC this or PDS that or such and such that, and we know the inclination angles of those, except that I would love to know how you know the inclination angles of those.
So I'm not the expert on this. I think somebody else could probably say better, but.
So if you can get the near-in jet, that ought to, so you can get its angle from some combination of watching blobs move and getting its radial velocity. Yes, he's going to shoot this idea down, but that ought to give you some inclination information.
Yes.
So I was also going to say Aaron and Chelsea might be able to comment on this, but inclination, my understanding is that inclination for disks is a hard problem and is not terribly well constrained to within 10, 20 degrees. I don't know if you have more to say, Aaron or Chelsea.
But 10% is already very good.
10% is
good, yeah.
I think if you have like if you're talking about a fairly high Eddington disk where you can measure lines, then you can get an inclination to within 10%. But if this is a low luminosity system, it's going to be harder.
What is that?
The iron one.
Oh,
The RK alpha.
So not broad emission happens. I was asking what that was based on because I was
Yeah,
Yeah.
so that was for the disk inclination that you can measure from the broad iron lines in the X-ray.
Okay.
So you can, I mean, you can look for broad, like H alpha, but that's going to be more. That's not going to be really necessarily the disk.
Yeah. And then, sorry, if you want to complicate things even more, of course, disks can be warped. So you might get one measurement of an inclination from an iron K alpha line telling you that the inner disk has this inclination. But if you have a disk warping, the outer disk could be at a completely different inclination angle. So you may have two inclinations that you have to worry about. So.
The other I think thing with this is that if the black holes are non-spinning, then that inclination will basically be unchanged right up from the point of formation up to the point of merger. If the black holes are spinning though, and that spin is misaligned, you're going to essentially get more and more precession as it loses orbital angular momentum, so that by the time it merges, your orbit might actually be pointed in a completely different direction than your AGN disk.
But can you get inclination information from that precession if you're seeing it in the waveform? So, oh, maybe.
So the inclination, the orientation, the angle between the total angular momentum, if you have a lot of precession, can be determined. The question is that something that's going to be imprinted, or the spins can be misaligned, in which case you'll have no idea. It'll be wherever you were on the precession cone in the past. So you can measure J, and the orientation between J and line of sight. And if that's the thing that's relevant and encoded in the dynamics of the AGN disk, then yeah, that would be an indicator. But if the spins have been randomized by some other process, then it might not be, if that helps or not.
So I think it might help because I think, we would expect that the spins of the stellar mass black holes would come into alignment with the AGN disk over relatively short periods of time. They don't have to accrete that much mass to have their spins aligned. And so if that happens, then maybe we're good. And then I would also just comment that I think this is an excellent argument for aggressive funding of large collecting area X-ray missions, because as people who are not in the AGN community may or may not be aware, we have about, 300 nearby AGN that we can really clean up on, in the X-ray. Clean up on is probably an overgenerous term. But if we're going to get the inclination angles from the iron K alpha line, we need a lot bigger collecting area. And if we're going to get it from jets, the downside is that only about 10% of AGN actually display them. So that is another caveat. But obviously, if we're lucky, then it's better be lucky than good.
If you want to be even luckier, if the disk is edge-on and is mazing, then you would know the inclination.
Yes.
Yeah. Really, really, really lucky.
I have a question about that. Yeah, just very quickly. So I agree. I would like a wide field X-ray instrument as well. Let me just add that technically, if you localize something and there's one AGN within the localization, you can look at that one, right? And then you don't need wide field. But I'm gonna not say this because I want wide field X-ray.
On the inclinations, again, when it comes to planets, they may form, and they may be with the same inclination as the disk, like Jupiter, right? But collisions with other embryos will tilt them, as we know. Shouldn't the same thing happen also for black holes and AGN disks?
Yes. My statement was. Yes, my statement was purely that, so again, for folks who may not be coming from this community, the sort of back of the envelope numbers that I keep in my head are if you have a stellar mass, or if you have any black hole that's accreting at Eddington, it takes 40 megayears to double its mass. And so you might worry that it would take that time scale to bring the spins into alignment with the disk, but in fact it does not. It only needs to accrete like 1% of its mass, so it happens rapidly enough. But yes, there are other interactions that could muck that up, but you're not, on average, most things, especially massive things, are going to end up pretty okay.
I have a follow-up question. I was going to wait until other discussions to ask that, but since inclination has been brought up, apparently a test of the AGN model would be to check the spin rate of the incoming black holes. Apparently, whenever they merge, the chi factor would be always 0.7, right? So, so that would lead, right, to a... huh?
Yeah. Sorry. Wait, what are we talking about? Like repeated mergers of black holes, or?
Yeah, if they merge, right?
Not chi effective. Isn't it the A, which is the final spin?
Yeah.
Set to 0.7.
Yeah. Sure. Yeah. But and there's this. You've worked on repeated mergers, so there's a universal.
Wait. Wait for me.
Do a dance, Richard.
Oh, I can't do a dance for this. I don't know a dance for this one. Coming together and then forming a big spin. Not really a dance move. Yeah. So when you have repeated mergers, you will tend to form black holes of larger spin. And when you repeat this process hierarchically, there's a universal-ish spin distribution that you would converge to if you had an infinite number of hierarchical mergers. And it happens pretty quickly, and people like Carl know this because they worked on it. But what is, so you're saying you want to use this as a signature for hierarchical mergers? Yeah, you would also get mass ratio features in the mass ratio distribution, the spin distribution.
No, I'm saying that because there was a criticism that I heard that the spin rate of sorry. No, yeah, I'm bringing this up because that was a criticism that I once got about the model, that there are observations, right, that show that that may not be the case.
Getting shy, Richard.
Well,
I'll walk around. Okay. Make it easier for folks. Yeah. There are 10 events. 10 does not mean that they don't exist.
Also,
So, yeah, and they could be strongly misaligned, and then they would be perfectly consistent with what you see. So we know that there's not lots of events that have spins of 1 like this, because none of them are consistent with that. They could be misaligned. It starts to get unlikely that they're all big and random, because then we ought to have seen one pointing up once in a while. So we think they might be small, but with 10 events, I mean, come on. And many other people. You're in charge.
All right. Go ahead. I think Charles can say something.
But also, I mean, we do have 2 events that have non-zero spin, and one of them is like fully consistent with having gone through a hierarchical merger. So one of them has a chi effective of roughly 0.4, and that's the one with the largest mass ratio and the largest mass to date. Yeah. So if you want to promote hierarchical mergers and annoy some field population synthesizers, which is how I like to spend my time, then it's fully consistent. Okay. See, it worked.
Okay.
Okay, yeah, so and I would also say that right, that so yeah, with 10 events, there are some that are not low spin, and Barry has a plot that I think he's going to show later of what the chi effective is, right? And so as Richard has already pointed out, low chi effective, which is what LIGO actually measures, is not the same as low spin. At some point, obviously, we should see a very large chi effective if it's just because they're randomly misaligned. But the other thing that happens in AGN disk mergers that is not so common in like a nuclear star cluster, as a gas-free nuclear star cluster, is Amy's simulations have shown that you can form these new binaries that did not exist from singletons in about half the time. They come together in a way that is retrograde compared to the gas flow around the AGN disk. And so what that means is that when that binary coalesces, its spin is going to be negative 0.7 on average. And it's going to be hanging around in the disk, and there will be some other fraction of objects that will be positive 0.7. And so it's not so pathological to hope that there's a whole bunch of those things, and it doesn't actually, in an AGN disk, in another environment, that would be a lot of special pleading, but in an AGN disk, it's actually kind of what you would expect. And so we have they get what?
Do they get kicked out after merger?
Even if they get kicked out, they're not going to go very far, right? Because you're in a deep potential well, and you're also in the middle of a gas disk.
It cancels the kick, doesn't it?
No, it doesn't, because the orbital.
The biggest kicks are like this.
No, biggest kick is like this. I think up and down cancels it, doesn't it?
Oh, it cancels the. Sorry, not.
Depending on the mass ratio.
Yeah.
All right.
Okay, Richard did it.
Okay, so I was going to comment on something. So we both know what's going on with the hierarchical merger thing. So, and that'll be clear too. But I want to comment on this because I also think it's cool. Some of these are going to be unstable to purely relativistic effects and have to go through wild spin oscillations. So just because it's like this doesn't mean it's going to stay like this. Perfect alignment for certain mass ratios is not actually perfectly conserved. So that would also fix some of these problems as well, which is cool. I like it.
I just wanted to ask something here with this hierarchy. So if you postulate that, maybe this is something that's coming out that I'm not aware of, but I mean, if you just postulate that all of the LIGO black holes are part of a hierarchical merger chain, I mean, don't you run into problems? I mean, we should see. You're squinting. Okay, sorry about this, but I expect there'd be many more massive ones above the parent stability gap, but we would have seen them by now. But
In a spin distribution would be hard to.
oh, okay, maybe okay. So I guess, and I'm wondering if you think of it that way, is there's a steady flux of building these things up. I mean, can we constrain what fraction of the LIGO sources?
We constrain them in nuclear star clusters. So Fabio has a paper on this.
Basically, it depends on the sort of escape speed of the environment you're building up in. If it's an AGN disk or nuclear star cluster, then you can have this sort of steady state flux where you have a lot of like low mass black holes come in and you're building second, third, fourth generation. In wimpier clusters like globulars, the escape speed is such that you can retain up to one generation if they're non-spinning to begin with. So if all black holes are born with low spin, like LIGO has kind of been suggesting, then you can build up to a second generation that'll maybe populate one step into the pulsational parent stability gap and give you some spins. But you can't really get past second generation because then the radiation recoil knocks you clean out of the cluster.
What about in AGN?
AGN, I think, would be super cool. That's part of the reason I like this channel so much, because not only that, but then you bring them back down into the disk, you start combining them, and you get all this weird, like, black holotesimals, like, merging repeatedly. I think there's a lot of cool stuff you can do there.
Yeah.
So I was also going to say that ongoing LIGO upper limits on mass is really cool for AGN because that forces you to put an upper limit to the AGN lifetime if you want to say all of these mergers are happening in AGN disks, right? So we can really do damage to our models of AGN disks by the LIGO upper limits on mass. So that's cool. So if I can't remember who it was presented the short time scale, was it Aaron? Where some people think that AGN are these sort of short episodes of instability from a fuel source. So you get a disk that lasts, 0.1, 0.2 mega years. If that's the case, then you'll get a burst of mergers of the black holes in the disk, and they'll be kind of randomly aligned, chi-effective around 0, and then it's gone. So you might get 1 or 2 generations, but you're not going to get multiple repeated generations to build up really massive things, right?
Do you want to comment?
Well, I just wanted to add to what Carl just said. So what we find is that in globular clusters, actually you never get mergers with masses of about 100 solar masses, just because after one merger you kick all the black holes from the star cluster. And actually the only type of systems where you get multiple hierarchical mergers are nuclear star clusters. And in this case, the escape velocity above which you can actually form more massive black holes through this process is about 300 kilometers per second, which comes from the fact that the mean of the kick distribution for highly spinning black holes is around this value. So they, on average, they get kicks of about 300 kilometers per second. And this doesn't depend much also what we find on the initial spin distribution of the black holes and the initial distribution of the stellar masses, so the initial mass function that you use, and the metallicity of the environment. So the mass function also of the black holes. And so the other piece of information I wanted to add is that so I would wear the optimistic hat, is that we actually do observe nuclear clusters with these properties. I don't know if they have a supermassive black hole or not. They do have some of them star formation going on in the center. But we do observe nuclear clusters with about 10% of them with escape velocities that are larger than 300 kilometers per second. And in these systems, you would see this hierarchical merger process occurring between black holes.
Last comment before the coffee break.
Oh, yeah. Sorry, just.
Well, no, you go ahead. I
Okay.
want to refer to something that Barry said, but go ahead.
Just very briefly, one of the reasons this is really cool in the AGN disks, right, is like if you're around a 10 to the 8 solar mass black hole and you're at 300 RG, that's 12,000 kilometers a second Keplerian. So even if you get a maximum extremal kick, like you're not migrating that far out of the disk. Exactly. So you might end up with this cool case where like a few of them will get punted into the supermassive black hole as like Emery sources, and then afterwards you've built up this sort of IMBH thing after the disk dissipates. So there's a lot of cool stuff you can do in this channel.
Very last comment.
So something that you said that reminded me in terms of the AGN lifetimes. The AGN lifetime is not necessarily the disk lifetime. So you may have disks there for an incredibly long time, but for whatever reason, the black hole isn't accreting, very much like our own supermassive black holes. We have red giants dropping tons of gas on our own black hole here. None of it seems to be accreting. So on the more optimistic side, these disks can be facilitating mergers for a long time, but the AGN isn't lit at that point.
Okay, so I think there are other times, so we have to get coffee now. And after coffee, we can continue. There are 2 more slides to discuss, and then turn over to the future, what we want to see in the future. Okay, so we reconvene at 3:30.
3:30, yeah.
Okay then. All right, so at 3:30.
Jillian is walking in with some really cool pants.
Yeah, that was true. That was actually my
I was just like,
Analytically. I mean, yeah, it's like, I don't know, I just love the fact like plan information theory, but like also you build up.
I mean, like density profile.
The density profile. But I was going to say for type 2.
I mean, try to find something.
Yo no puedo salir, sí, entiendes, sí, yo salgo a 5:30.
The mass of the section.
But that would be cool because then.
Catch up. They also, I think the Zoom is being recorded. I don't know how to view the recording, but it says recorded.
It is recording.
Oh, okay.
So maybe in the future we'll be able to do that.
Yes. I don't know if we can currently do that.
That's fine. I'm busy right now.
Okay. You're living in the present.
Indeed. We'll have, we're going to basically have it up on the website.
Yes.
So the parts you missed. If you have the time and energy, you can go back and see it through it 4 times.
Probably do that.
But I know that
Several people.
Andrew's also.
Yeah, we got here early.
Oh, yeah.
Great.
I got here an hour earlier than I thought. Very efficient.
Expecting to get ready for
Yeah. Well, I had to stop home on my way. I had to stop home on my way. Oh, yeah, okay. What's the, I managed to jump back on a line with my not yet expired.
Sweet.
Oh, yeah. We're very close in, yeah. I would have to, let me pull up the paper so I can look, remind myself.
And you haven't accounted for the feedback from the black hole.
No, yeah, right, so exactly, so.
But like, and also, if you have 100 solar mass.
Right, so we're using the Circle and Goodman 2005 disk model, so, yeah.
I was trying to.
Neither do I,
I was trying to look it up in the paper, but I didn't find it.
If you give me a minute, I'll pull it up, and I remember where it would be mentioned, and if not, what's the exact number?
Lower. So this is.
But yeah, no, I mean, that's the biggest thing we're missing, and that's also the reason that we don't make any real statements about once they form binaries, what happens. So the feedback is important.
I know you have something that's
Right.
What's the initial before the yesterday?
Right. So.
Carry from there, but.
Right. Well, yes. Yeah. But
What we do?
That's terrible. Body resolution at that scale isn't great. So we're actually.
You want to say that they are captured?
Yeah. I have.
Yes. No. Of course.
I mean, I also have like.
The point is, yeah, the statement we can. I mean, I'm assuming you're asking the centricity of the orbit and. Right. Oh, okay. Sure. That is easy. Yeah. So I mean, we consider them merged when they are at mutual hill radius. So that would be.
They always form at the what's the initial?
Right. We're using So we're using that to define it as a binary.
So the gas hardening
In a
is.
sense, and actually you should follow Stephen Racing as a Racing for people that's information.
Sure.
The stable acquisition, we have the same ideas. Question again, did you capture it in the periods, did you capture it in the most separation, what separation is just.
Right,
So, okay, so what you're asking is, at what radius is it bound? Is that?
I mean, it does have a lot of
So
orbits.
right, you have the black holes coming on migrating,
Yeah.
then they stop and you start accumulating them until they totally interact, right?
Correct.
So first of all, so the drift away, right?
Yeah.
Oh, no, it's actually.
It wasn't clear to me whether in the interaction of all of the black holes together or
Yeah,
just
one over.
One of the plots just time history of 4 or 5 black holes.
Sure. So.
I saw the migration.
It takes hours.
A picture will be worth 1,000 words. That's great.
It's gone.
Yeah, just
And so
zoom
the
in on
thing is,
that.
basically, if you're never assume
Okay, sure.
because it won't be.
Okay, so this is,
I thought this is not of interest.
Yes,
okay, I'm sorry.
This is just showing how they migrate in their
Know that LIGO.
When they, okay.
And by
So
LIGO,
you did a measurement,
LIGO band, gravitational.
Well,
finding out whether or not they were coming in prograde retrograde.
right, exactly. I mean, yes. So not included in this paper, but in work that I've been working on more recently. Right, we actually track it past that point and we look at, we zoom in and look at the orbit. And so, I guess we haven't really specifically said what would be the semi-major axis of this binary. But we do look at, at what point do we not see do we see the binary
Right, very.
It comes in fast, right? Then there is strong interaction. What I am resisting is the basic calculation showing, and this is what I wanted to do when I wanted to calculate instead, is the energy dissipation looking to do will be important, right? Because this will tell you exactly the mind that you had about the energy versus the energy.
This is what CPA has been trying to compute, but not yet successfully.
This is what I don't understand. Even analytically, very simple calculation. So it should go, because I must say I'm less convinced. When I heard you first, I said, great. Now I'm less convinced. I don't see the actual formation of the binary space.
No, okay, here's what's going on.
The formation itself is a handling with this basic requirement, but it's not very clear to me.
Well, but we also have an energy requirement as well.
Yeah, this was
Right. Where we do,
But I don't see it. You have an energy requirement.
No, here's the problem, numerically. To actually track sufficiently finely the time, we have to dump extremely frequently all the positions, and that turns out to be challenging numerically. So right now we're dumping, 10 times. Well, we know inside the code, but we'd have to go in and rerun a model. And I'm not even sure how we would get that fine a time
So when you
resolution.
say you get a binary, you come to some separation, and you say, okay, it's more than the heat rate, and you calculate the relative velocity between.
Right, exactly, the kinetic versus binding it, relative kinetic versus binding it. So it's a 2-point confirmation.
I mean, ultimately, we're gonna have to zoom in on it.
Right, of
But
course,
the point
yeah.
is, it's not clear that you're gonna learn that much after a close encounter without the gas.
What?
Thank you. Also account for the heat
So that's okay.
You said the heat rate is discussed. But this is a combination. Just comes effectively right in by definition when it goes into the heat rate. As it goes in, it's not now, right? It cannot be.
Right.
Okay, just accelerate. Now you have the dissipation. This is why I don't understand. This is why I'm not sure I understand how you can get into the heat rate loop and become bound without calculating the actual dissipation during the.
Well, so the dissipation that we have now is, effective torques. So there are torques acting on these objects from the disk that are transferring energy into the disk. Now, these aren't the right ones. And the McFadden calculations are getting closer to the right ones, except that he's still fixing his binary orbit, so that's not right either. So this is actually going to be a very difficult problem to do, right? Because you actually need to consider both the global, the interaction with the Lindblad radius, but also the local interaction of like the co-orbital and maybe even disks of each object as they come close.
That's the simple calculation. You have the global. Sure. I'm fine with that.
Yeah.
You get a position they come close. Now you don't resolve it with that.
Right.
So, but you have the velocity just before that. You can calculate the first order. I'm not sure I agree that it's maybe complicated.
But how much energy would have to be lost to buy that?
Basically, this is just gas dynamics. The torques, this is the dynamics. The torques will not
Right, and that's, that we already have that data, right? We have the kinetic and the relative kinetic energy. That we know.
Otherwise, so we have the density, the basic calculation. What is the dissipation? Just to get it as this is the order. I find it not convincing that I don't see the binary. Say, four binaries, okay, the function of measures is a different question.
Right, yes, that's right.
I don't know. Even the formation, I feel like I'm convinced that I see the binary. Yes, you have this basic requirement, but it's not clear how you can resolve I was just doing it.
Yeah, I mean, I guess yes, we can do it, but it's not clear, honestly, whether it's going to be all that reliable, given if we're still continuing to apply the large-scale torque as our primary dissipation, even though you're close by. So there's, I think all we can say is that as you get close.
What surprised me, the large-scale torque.
If I send you my slide, you think you can just post it? Yeah.
It was my
Okay, that's a question. Yeah, I do it now. Yeah.
So if you were very good.
Yeah, very good.
And the time scale that you built, I don't care too much about this global torque.
Yeah,
I'm voting for this, fine.
But, well, but now let's see. You did one calculation where you used much smaller capture rate.
I tried putting.
Yes.
And did you actually get any antibodies going into orbit around each other in that calculation?
Yes, but remember we had this crazy centricity driving because we were using the large-scale torques and treating them still as singletons instead of a binary.
Yeah, but that's exactly what Haggai is asking about. So what we tended to get is binaries that form and then stretched out, got driven to extremely high eccentricities. So this was all in the end body.
It sounds like it's winching. Actually, very eccentric because the next state is
Then it falls,
they are disrupted.
Right, disrupted.
But, well, no, they didn't disrupt because they would have, they got within gravitational wave, fast.
Yeah, that's actually,
wave,
they became so eccentric that at Pericenter, probably gravitational wave radiation actually would have been. It would have emerged before it could get disrupted. If that eccentricity driving is correct. Yeah.
The question is like, let's say it's in order to get to a pericenter, do it on a nominal time scale. It's just a few, which means you need black holes.
I know.
To the Higgs
But that's, we don't understand that eccentricity driving either.
Which is why we didn't include it, yeah.
Eccentricity driving, I can understand, but not close pericenter. But you can have really high eccentricity, just the semi-direct is also high.
Is also high, yes.
No,
yes.
well, the semi-major axis may have been high, but the
I want to see the
pericenter.
Okay, I want to see the pericenter. Show me the pericenter.
Right, but since we don't have the physics to do that correctly, so we're just
the gravitational wave stuff easy.
Oh well, it may be easy, but we haven't put it in yet. And also, but getting it there. No. But the point is, the physics driving that eccentricity is not. It's not clear that we have the right physics in the antibodies. Because the only thing we've got is the torque. So that's what's driving it by definition. And since that model, there's no reason to rely on that. Now, your argument is good, but that would say that this eccentricity driving is essentially not correct.
Maybe since you don't resolve the antibody readily.
But actually, I ended up.
Well, I mean, we've resolved it numerically. It's just that we don't have physics at that scale yet appropriate because we're relying on large. We don't have the core.
If you resolve it, you see the binary. You have a binary.
Yeah.
Yes, and we see that. Yes, of course we see that. Yes.
So you have the initial binary.
Yeah, well,
I would like
sure.
to see, but the binary. Okay.
So we could tell you that, but then we would have to tell you that it wasn't right.
What you say you see it, but then you see the eccentricity grow.
Yeah, but also, and therefore we don't.
At the same time, it's
But we are right. But the thing is, no, because the thing is, we don't have the physics that are right, the cobordor disk, or right, like the gas feedback. Once you're within a Hill radius, those things are more important than the global, right? But we only
We're not even
global.
Well, you know, we're not even talking about gas, which ought to be vital.
Yeah, this is first question.
Right. So we could put that in, but the point is, at this point, it's not correct
it's a gas dynamics
anyway,
problem.
so it's a.
And really, it's a gas dynamics problem, which we're making with an n-body code, and it's a very nice fade. But the questions you're asking are now, the questions you're asking are taking us into the realm where we really do need to do the gas dynamics, which, you know, Betsy is doing the first steps of, but ultimately we're going to have to probably use something like Disco to dive into that. Your questions are perfectly correct.
It's an important step to do. I'm saying I'm not sure.
Yeah, it's the first step, it's not the last step. Sure, right, we believe it. We're just saying we can make it energy, and we can make it energy and a semi-major isotope.
How do you decide on the traffic?
Where the migration traffic is?
This is an open question.
Okay, so Jillian worked on that in Flywire as well, but what it comes back down to is back in 2012, Particle et al. Showed that the direction of migration depends on the local entropy gradient. And the local entropy and vorticity, that is specific vorticity. And so as those vary, you'll get inwards or outwards migration. So we took sort of classical disk models, Sirko and Goodman, Thompson, Clutter, and Murray, and just took them at face value and asked.
All the way to the
and so we got our traps are at like 600 AU, something like that.
600-700 AU,
Yeah. So, is that 50 or 80?
So for the Circle and Goodman, I believe there's one at 50 RG and one at like 700.
Yeah, okay, that's right. So, in some sense, it's very naive because these models were not developed to actually produce, good thermodynamics, which is what we really need. But that's why we're having this conference, to start getting people to think about that question. But right now, the traps are based on sort of dynamical models and what the implication would be, given what we know about migration directions.
There is. What is operation time?
Operation time for
binary and the message.
I was gonna say the.
They tend to merge before anything else can happen.
And then you can't do it from.
Right, we don't really.
I'm asking about it.
Exactly, right.
So the evaporation time scale overall now, what you tend to be 8.
Yeah, for the supermassive black hole, yes.
So it's very hard to get them out of the disk.
So what I'm saying is, at the helium,
There's so many
soft.
Compared to the thermal velocity. Well, except it's not an isotropic distribution, even close.
Your stuff is not an isotropic, but it's found inside.
Well, it's not found inside a nucleus because any star that's coming down that close is going to get its inclination reduced so that it's also trapped.
But
if you're close to the disk, yes, you have some, right?
No, but even if you're fairly vertical, every time you pass through the disk, you're losing angular momentum, energy from the vertical motion, and so that brings it down.
Not very large distance.
Right, if you're on some sort of plunging line.
So okay,
So your point is there's certainly going to be high velocity stars.
Right, and yes, it would be, they would be solved to that, yeah.
Yeah.
We do a calculation for if you're in the disk.
I think Nathan actually did the disk is fine.
Right, of course, it's going to be very small, exactly. Right, but it's cheating.
This is the question you may want to ask Nathan, because he did think about that. And I seem to think he came up with an answer that it was pretty hard for a three-body interaction to happen. I don't remember the calculation. So we may want to try and... Is he still on?
Probably.
I think it's evaporation.
I could turn...
Maybe it's evaporation kind of speculation.
He's on, but he's not.
He's not in front
It's
of
an
the
empty
camera.
chair.
Yes.
Either way.
But you could mention, like,
Side
mention to him
So one is about the distribution of masses of the 30 solar mass black hole. So paper about mass derivation. These will be actually the prominent ones.
the ones who would come down.
Yes, it's even larger than
All right, that's actually interesting. Yeah, because we're just using a naive IMF, but.
Krupa is probably terribly wrong. Especially
Yeah. Oh, I mean, agree. Yes.
Especially because no way they would find money. Right? So they had to put somewhere else.
Sure.
And therefore you get segregation.
Yeah. Okay, that's actually a very interesting point. Yeah, we should.
Oh, okay. No, that's my point. Some of these, a lot of these actually.
That's an operation. Actually, one That's about hyperboxy stars. Anyway, so I would be a bit clear about the number of and well, information is I agree. Something to show.
Yeah.
Yeah.
I was hoping I didn't think about the integration priming. I don't think about general existing larger scale.
Yeah.
So it's more general, which I'm not sure actually doesn't would be enough. Exactly. Where it is.
Yeah, no, you want to bring them all together as well.
So yeah, in your case, maybe it could be very, very small velocities.
Right, exactly. That's, we've already set up that situation.
What we're working on now, though, is the one thing that really ruins all this. In addition to the ones coming in from high inclination, you also have retrograde orbiters because you're in Gen now, and those are going to have really high relative velocities. So which we're working on now, but it's an issue. Exactly. Right.
So, on the other hand, the retrograde orbiters may go by so fast that it doesn't matter.
Because you want then disruption to get too deep, which would be even larger, much larger for the retrograde. So I would think that you have in mind.
You might just go through and chew up everything.
It would completely kill the resonance change.
But it will certainly. Well,
which that actually might help.
Actually,
we have a lot of evidence.
The resonant chains get killed by the disk turbulence. This is something that I'm not seeing people model who are doing these resonant chain models. They all seem to assume a laminar disk. But like Nelson already showed years ago, that the disk turbulence sends you on a random route.
People have it. Look at even the recent paper, right? I don't remember the first one.
Yeah.
Sean Raymond is on that.
Yeah.
That's very recently discussed also.
This was like just in the last few weeks. Yeah. I saw that too, and I was saying, I have to write them and say, well, what about the turbulence? Because we put turbulence in, and otherwise we wouldn't get mergers, because you would just everything would get trapped in resonances. We see that too. We don't have turbulence, but a turbulence of alpha 0.01, which is neat anyway, that's enough to disrupt it.
They're really unconscious.
I would think you might have motives, not just two of them coming together. Once you start the system, start having all these collisions. That's another way of doing it. You might get to something which is quasi-stable, then...
Yeah, no, actually, you do. I mean, we've been looking at that, because these initial models, we start with 10 and with however many, but we've been looking at new models where you have more coming in over time, because more will migrate in over time. And when you get that, right, you have these stable configurations, and eventually you set up a chain of events. Relative inclinations. So we're working. Yeah. Our problem is we have a one-dimensional disk, so we're only using very small configurations, but other people are looking at higher. Yeah. So this is 2D, but it's well, most AGN disk models are one-dimensional.
Yeah, but they care about age and talk about the overall.
Her, but I don't want her to be creeped out, so I don't want to tell her.
I lost her not by and now I can't see them anymore.
Not that big.
Sure, it's not like a month, right? But now I know when we just put it back on.
So we're, right. Right, so technically it is a 3D simulation, but they're all pretty much coplanar by the time they come into contact, because we give them small inclinations to start out, and by the time of their what? Yeah, exactly. So, I know, it's not fun, but yeah, Well, but also, we are only looking at the 1,000 AUs a day, so you could say that anything that gets ground down outside there will be coplanar if it makes it that far outside.
One thought that they use it was 8 over I is typically like 5%. You still get 50 AUs, which is much larger than your real.
Yes.
It's almost the time you're giving.
For the hill values and the binders, it's just a few AU. It's,
50 AUs is what it
is, yeah, okay, sorry.
So you do care about it. And it's also the factor of resonance capturing.
Okay, so let's continue with the discussion. And so we have a couple of more slides to discuss, but we have to keep it a little bit shorter. So something like 5 minutes of discussion per topic plus 5 minutes questions per topic. And then we should move on to discuss what you all want to see in the future in the next 2 to 5 years. So discuss some open questions and what, set the agenda what to do next. So let's start with the Start This project, which was recommended by.
Thank you very much, Spencer. My name is Bektaulya Shukirgaliyev. I am now a postdoc in Heidelberg University, but soon moving back to Kazakhstan. So what I would like to talk about is this the StarDisk project, we call it. So we are doing direct n-body simulations of AGN dynamics. So that is, we combine solar type stars dynamics with the static Shakura-Sinaev AGN disk, accretion disk, and then we look at the mass growth of the black hole, supermassive black hole, and how the stars accrete and the orbital parameters of stars in AGN. So from the disk we take into account only the drag force, and we have found that this existence of the accretion disk increased the accretion rate of the stars onto the supermassive black hole factor of 4. And then mostly this drag force would align this accreting stars onto the accretion disk plane. And they mostly, like almost half of the accreted stars accrete on the really zero inclination with the disk. And then also the circularization of that accreting stars happening with the drag force only. So that is what I wanted to present quickly. So the references are given in the bottom of the slide. And now this project is still ongoing, and we are going to take into account the stellar evolution on our modules. So thank you.
Do you have any questions or comments?
Have you extended this to black hole ground-down? So assuming some sort of accretion as they punch through the disk, grinding them down? Or is this just stars?
So in this case, we have equal mass stars. So we treat them as a solar type stars only, and they come to the central supermassive black hole. So we don't really see this tidal disruption event, but we assume that we have some kind of radius. We call it accretion radius, but it is still much larger than the Schwarzschild radius. And when any star comes into the this radius, we assume that this is accreted, and we put all mass onto the supermassive black hole.
You can basically generalize your results by just extending the star capture with the Bondi accretion, and then you can
and
see
then that is captured. So the accretion disk helps to increase the rate of stellar accretion. So this, for example, in this right-hand side, there is this dotted line, which is when there is no accretion disk. So this is the growth of the supermassive black hole as a function of time given in relaxation times. So then this the colored lines shows when we have accretion disk. So it's factor of like 4 in the accretion rate goes up when there is the drag force acting on the stars.
Vince, you're saying that you could use the Bondi accretion radius instead of black hole. Your question was, or your suggestion was, you could use the Bondi accretion radius to set the drag force for a black hole,
Yes.
right? Yes.
Yeah, because in your calculation you only assume the hydrodynamic drag, and you take just the size of the star to be
Yes, actually,
the
only
area.
the cross section of the stars is taken into account, and only we change the momentum of the stars when they cross the accretion disk only.
How, what's the linear size of the accretion disk? Where do you cut it off, and how large is your nuclear? I mean, I see the masses, but what's the size of them?
So we use actually for the size we use influence radius of the central mass black hole. The influence radius. So where the stellar mass in stars equal to the mass of initial black hole mass. So this is the size for the accretion disk we put onto our models. Okay. And that is, and for the stellar cluster we use Plummer model, so it could be any, yeah. So then we use it in n-body units, then we rescale it to the real systems using the influence radius and the mass of the supermassive black hole.
Have you considered using something more complicated than a Shakura-Sunyaev gas disk?
Well,
or how hard would that be?
By now not, but in plan we want to put some leaf disk really.
I'm sorry.
Yeah, so by now we just use Shakura-Sunyaev disk only, but in the future probably we will use some real leaf disks. But yeah, we will consider it.
Yeah, I think one of the problems with that is that just the chance quadruple momentum of the stars warps the disk. So you expect the disk to be not flat if they interact gravitationally with the stars.
Yes, that could be
a complication.
Yeah, I was wondering this dynamical friction force that you put there when the star passes through the disk. Yes. You're considering only the mass that is interacting directly with the stars. So you're not considering like the formation of a wake, or okay, because dynamical friction will be stronger because it will take all the weight, but will not be directly. I think that the typical dynamical friction, because you have a very finite size of the disk, so then you will cut in a strange way the wake. So the force also will be different. I don't know if someone know something about dynamical friction in finite spaces, because then you have the logarithm, the Coulomb logarithm, and it's difficult to estimate. I don't know.
Sure, that has been done before. I was gonna. Sorry. Yeah, I was gonna ask that too, because the assumption of drag in that way, that's not actually the physics that happens there, right? What is actually happening is the equivalent to type 1 migration. You have a friction that is due to the wake of the orbiter. So Hanno Ryan has a paper from 2012 that he calculates that. He compares this drag with the friction from the wake, and he gives some numbers here. For an orbiter of mass ratio 10 to the minus 5 and 10 to the minus 4, the dynamical friction dominates up to a factor 100. I would like to see that work also for that form of friction. Because you see that also, right, from your equation there, if the orbiter follows the gas disk, the drag cancels out, right? Which is not what happens for migration.
No, but you can actually get them to be more or less the same. If you do the gas dynamic friction, but you account for both the outer and the inner part, okay, which have different velocities, okay, then you can actually get back something which is very similar to the torque formulation.
Oh, sure, yeah.
And then you get, and certainly you don't get zero, so you actually get back. So you actually, if you do it correctly in that sense, you can get it fine. Now, for the going into the disk, then you don't care about the torque stuff. It's dynamic friction high on eccentric orbits. Only when you get into the disk itself, then I would agree that you should be more careful on how to do it.
Well, Hanno calculated it.
Yeah, we calculated too, the same thing.
Sure, yeah. Oh.
Yeah, I was just going to say, and this is, I mean, I think this is relevant to the gas drag, but even more so if you're going to try to compute the vertical perturbations and include some kind of migration torque, is that I think observationally AGN disks are not razor thin, and the fact that they are not razor thin has some serious implications for this, right? So if you've got some scale height that's, you know, for the aspect ratio is 0.05 or 0.1, which is definitely very consistent with current observations. That's, in fact, I would say, like, for example, the timescale variability leads us to suspect that we have relatively thick disks. Then obviously you're going to encounter a different velocity field at a, you know, a scale height above the disk, and there's lots of other consequences. So I would say, even if the objects, even if the orbiters are going to perturb the disk, I would consider trying to put in a fatter disk somehow.
Okay, thanks everyone. We should move on to the next topic. The other question is, if you have some anisotropy, does it increase or decrease the merger rates?
Thanks. I'm Hiroshi Tagawa, a postdoc in Edubeishi University. So yeah, my interest is what is anisotropy for black hole velocity distribution in the quiescent phase. And as Bence explained, the angular momentum of more massive object tend to align to total angular momentum of the system. But the degree of anisotropy would depend on the mass distribution and the angular momentum distribution of the system, which would be strongly influenced by formation scenario of nuclear star clusters. So yeah, it's not obvious what is anisotropy for black holes, I think. And recently we performed the n-body simulations using a semi-analytical model, and we find that the merger rate in the AGN disk strongly depend on the anisotropy of black holes. And the figure shows that the y-axis shows that fraction of mergers in the AGN disks over the initial black hole number crossing the AGN disks, and the x-axis represents the anisotropy for black hole velocity, which determines the dispersion of initial relative velocity compared to the local AGN motion. And the different color in the figure shows the mergers from binaries formed by different mechanisms. So, yeah, as discussed earlier, binary can be formed by dynamically and gas effect. And we find that gas capture binaries and dynamically formed binaries mergers from these formation channel strongly depend on the anisotropic parameters. And this is because these binary can formed within the AGN disks. And actually, the capture fraction of black holes to AGN disks can well constrain this merger rate. The capture fraction is shown in the brown lines, and this quantity is estimated by time scale for the capture by gas dynamical friction, which is strongly dependent on the initial relative velocity, and whose dependence is 4. So, yeah, I think it is important to unveil the anisotropy for black holes.
Questions with this?
That's a question. I'm not sure I understood what's the initial distribution of each one of these type of binaries. So you show, you have these different cases. So what do you assume for each one? I guess pre-existing or just in the disk, I guess, right? But what do you assume for this dynamically formed as the gas catcher? I just not sure I understood the configuration.
We simulate it, right?
Oh yes, we simulate the evolution of velocity of each black holes, and yeah, each black holes initially have some relative velocities, which is given by beta parameters. So most of them are outside of the AGN disks, and yeah, they can align to the AGN disk and then form a binaries.
You basically simulate what happens, and this is what comes out. So a number of objects form binaries in gas, just because gas can carry the initial energy, and then depending on what the velocity and isotropy is, you get different merger fractions. Can move on to we have a couple of more topics. Dan has a simple slide.
Oh, excellent. Like it.
Yeah.
So this was my slide before I saw Aaron and Chelsea's talk. But I elaborated on it a little bit, so. Oops, wrong way. Okay, so there's a lot more actually, but my point is that what we're talking about is essentially taking, well, there could be a few things we're talking about. We're taking the dynamical formation channel, we have a cluster of black holes, putting some gas around them and asking, how does this formation scenario change? And so an interesting question to ask is, how much gas do we need to change the outcome, so merger rates, orbital eccentricities, the observables, and given the answer to that question, what is the observational thing we're looking at? Is it always an AGN? Are they different types of, will different types of AGN give you different outcomes? Probably a hot, puffy, advection-dominated accretion has a different type of disk than the Securus Shenyaev solutions. And so I just think I just wanted to put this slide up to keep this in mind. And it's come up a few times already. A guy mentioned you could have no black hole. And we talked about the AGN could be quiescent, yet there's still gas there. So, and this is important not only for rates and parameters, but also when you're trying to localize a LIGO or LISA event on the sky and trying to stick it to an AGN. Maybe there are different types of AGN that would do different things. So.
Anyone wants to respond to this? Sure.
Thank you, Dan. These are the questions that keep me awake at night. I'm gonna say, so one thing that I think I can say with some confidence is that I care about any gas cloud that has a density of at least 10 to the minus 13 grams per cc. And that's because, and I don't know if this came up this morning, but there's a Barreto paper from 2013, I think, simulating the hardening of a binary in our own galactic nucleus. In fact, they were modeling two O stars, but they were modeling them just as gravitational objects, so they're no different than two stellar mass black holes around Sag A star. And they found that at a density of 10 to the minus 13 grams per cc, their merger, or their hardening and the shrinking of their semi-major axis was sufficiently fast that I have a slide about it that I'm going to present later, and that the LISA people blanched when I showed it to them. So that's one thing.
I'm sorry, what was the actual conclusion of these?
They'll merge in it. Now, again, you're extrapolating, but they'll merge in of order hours, 56 or 11, depending on whether they are orbiting prograde or retrograde through the medium, or they'll move from the LISA band to the LIGO band in that time period.
Assuming a rate of hardening that is.
Assuming a rate of hardening that is continuous all the way down, which is not probably, okay, all of these caveats, but not, but 10 to the minus 13 is enough to make the binary have its orbital semi-major axis in 1,000 orbits for a prograde or 200 orbits for a retrograde orbiter. And that's a big change in a short period of time. Yeah, around its own center of mass. Yeah, 1,000 orbits around its own center of mass, or 200 orbits around its own center of mass. So this is very fast. And that's, that's not a super crazy high density. So that's one thought that I have to say. And then, yes, the thing that actually keeps me awake at night is this last thing, or the second to last thing, is what if a gas disk of 10 to the minus 13 grams per cc has no electromagnetic signature that distinguishes it from anything else? What if it's not accreting and it just sits there? And then we can't use Imri's fabulously clever statistical technique because we don't even know what to call an AGN. So.
Have you checked how this merger timescale depends on the location where you put the binary within the trapezoidal disk?
But it's very fast anyway in our model. Yeah, so it doesn't matter. So it's nice and fast. Yeah. So we don't need to worry about that for that model at least. I mean, Andrew may come up with more pessimistic models, but for we checked two different models, and for both of them it was really fast within 1 million years.
Maybe for ADAPS it would be worse. But who knows? We haven't checked.
I'm sorry. So ADAP is. I mean, you're losing angular momentum to the gas that's far from you, right? So it's not actual accretion onto the black holes, right? You're creating these waves in a disk. So I don't think that ADAP in this case would matter.
So one of the main things we found is that it's not that there is a torque due to waves in the circumbinary disk, but that's subdominant. The bulk of the torques are from very nearby gas orbiting in the mini disks.
Yeah. If they have mini disks.
But it's the gas in the Hill sphere, dude.
Yeah. So Andrew, the other question I had actually before was that how fast is the development of this this gap, right? Like if you just put in the black holes, they will initially move in a continuous gas, right? So this will take some time to open that gap. So I'm wondering if you will have, if that time frame is comparable or longer than the actual merger time if you start off in a uniform gas, essentially. Is this something you guys know?
No. So it's an interesting thing. It depends on the viscosity of the gas. But so you're talking about type 1 protoplanetary, like if you just have gas that's there and hasn't been cleared out yet. I don't know the exact number, but typically a cavity or a gap can form in hundreds of orbits, maybe 1,000 at low viscosity. So yeah, that might give you enough. Yeah. Okay. So that might work.
Comments? If not, then let's move on to Fabio's topic. Do you want to discuss this? Or?
Do you have also put the other one?
Yeah.
Is it the next one?
It's not the next. We come back to the other one.
Okay, well, this is just a plot of the half mass radius versus mass for all type of clusters in the local universe. So you have in blue, you have globular clusters. Black points are nuclear clusters for which we don't have any idea of whether they have a supermassive black hole or not. Purple points are nuclear clusters with a massive black hole, either an AGN or a dynamical measurement of a massive black hole, and orange points are nuclear clusters with an upper limit to the massive black hole. And so the box bottom right, the solid red lines, indicate the region within which you would expect the hierarchical growth process that we have discussed before to occur. So again, you need escape velocities larger than about 300 kilometers per second, which corresponds to these very massive clusters, about 10 to the 7 solar masses, and half mass radii less than a few parsec. And as you can see, there is a small fraction, but there is some of the nuclear clusters in the local universe where you would expect this process to occur. And we estimated based on this also an approximation of a merger rate and of let's say binary black hole mergers above 100 solar masses, which can only be produced by this model, either binary evolution in the field or formation in globular clusters cannot produce binary black hole mergers larger than 100 solar masses because of pair instability supernova. And so we find a merger rate which corresponds approximately to one merger above 100 solar masses from these systems every a few years with LIGO. And this is derived assuming that all these clusters do not have a massive black hole. And so one thing I wanted to point out is that, again, there are, so to keep in mind that there is a variety of nuclear clusters or galactic nuclei, and also nuclear clusters without a supermassive black hole are really interesting. And in fact, this process might, for example, lead to the formation of supermassive black hole seeds, and therefore could also shed some light on the other type of systems, so studying the hierarchical growth process of black holes in nuclear clusters without a massive black hole might actually shed light on the formation of the central objects in the other clusters where we do see massive black holes. And that's what I wanted to say about this.
Thanks, Fabio. Any comments, questions?
So one of the nice things you can have is following a binary merger, binary massive black hole mergers, right? If you have this gravitational wave kick of the massive black hole, then we are left with a nuclear cluster without supermassive black hole. It's scoured a bit, but it might be enough actually to give us this. And it could be, in principle, could be relatively dense. Depends on how the time scale it took for the merger and the scouring, etc. But you actually could actually have this even in cases where you started with a massive black hole in some sense.
So something that I don't think has been mentioned so far, so in lambda CDM, we expect these hierarchical mergers to happen from mergers of galaxies with each other. And so we expect a population of lesser supermassive black holes and galactic nuclei. One thing we haven't really talked about is the effect, the scouring effect of additional supermassive black holes. Essentially, you know, very small, focused globular clusters that are completely dark. You throw them in, what effect will that have on the population of stellar mass black holes in the galactic nucleus? So if SMBHs that are in spiraling biodynamic friction stall at about 10 parsecs or a few parsecs, then maybe they won't impact the central population of stellar mass black holes. But if maybe they exchange angular momentum with some of these populations that you're considering, and that's how mergers happen, maybe that's a driver of mergers in lambda CDM, and that's worth pushing.
Okay, so if there are no more comments, let's transition to talking about what you want to see in the future and what are the big open questions to answer. And so I received some slides about this as well from Kaya.
Yes. So can you go to the next slide? Yeah, so going back to our galaxy, I picked up two questions relevant to gravitational wave detection. So my understanding is that if we detect a black hole LMXB binaries in the center, you can use that number and then also the luminosity function distribution, and then you can infer the total number of black hole LMXBs, including faint ones, and then using more recent models developed by Benz or Genezarov et al., we can estimate the isolated the number of isolated black holes, which can be used by someone like Barry, and then estimate the number of gravitational wave event from other galaxies. So that's a very nice coherent story. But can we do the same thing for HMXBs? Because my understanding is the HMXBs can be also good candidates for gravitational wave events. So what's the situation right now in our galaxy? So the Integral X-ray telescope has surveyed the entire galaxy, and they detected about 40 to 50 HMXBs. Most of them are neutron stellar HMXBs, and you can see the luminosity function on the right. And then, but it's stopping at some luminosity, as you can see. And then if you extend the log n log s, log n log l, and then you may expect more HMXBs. So that's where NuSTAR came in and trying to follow up some of the unidentified hard X-ray sources detected by Integral, hoping to find the fainter HMXBs. And then so far, we found none. Okay, so that may indicate maybe there is no faint HMXBs, or maybe this is due to the lack of complete survey or something, but TBD. On the other hand, if you go to the galactic center, especially talking about the central 10 parsecs, we do find a lot of magnetic CBs, we do find LMXBs, but based on the detailed Chandra plus IR source studies, there has been no HMXBs detected. So that's another no result. Then if you look away from the the Sagittarius star, somewhere around 50 to 100 parsecs away, we detected 3 HMXBs using the NuSTAR hard X-ray sources, and then Chandra positions, and then correlated them with IR sources. I'm not going to tell you which HMXBs because we are writing a paper soon, but that's it. Okay, so is this something you care? How many HMXBs do we have in our galaxy, which can be used for other galaxies, and then estimate the galactic wave events? Is this something interesting? Is this something people are modeling in this room? I just like to know. Or should I stop looking for HMXBs? Just to motivate my own project. So.
Fortunately, Guy Metzger left.
Right. I was talking to him during the lunchtime, and he was interested. He was puzzled. We should look into this program. So I talked to him. But does anyone work on this program in this room? But not yet. Okay. 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 So let's go to the next slide. Another class of objects maybe related to gravitational wave events is outer compact X-ray binaries, they have a very short orbital period, like probably less than 1 hour. And then you should have a hydrogen per star, because hydrogen-rich star, regular stars cannot just fit into the Rogerov, so that's how it works. And that means you just don't have enough, high accretion rate. So I was talking about very faint X-ray binaries, very faint X-ray transients in the morning. So these are the X-ray transients with lower peak luminosity, below 10 to the 36 ergs per second, maybe down to 10 to the 34 ergs per second. And since the Galactic Center has been monitored by Swift telescope every day, we detected 9 VFXTs so far. Okay, so that's outnumbers any other places in our galaxy. But what are these sources? And then one possibility is outer compact X-ray binaries. So when VFXT happens next time, I'm going to ask for more telescope time and look for short orbital period for the evidence, okay? But so far, no evidence, okay? But if we find one or few UCXBs in the Galactic Center, maybe that can tell us something about the gravitational wave events, for other galaxies. Maybe that's something interesting. And not just that, maybe there's something about the binary formation, as I was hearing about the soft versus hard sources. So this is probably hard sources, so they don't get destroyed by other stars in a crowded Galactic Center region. Maybe there's a bias toward making more UCXBs in the Galactic Center. So maybe that's something more interesting. So is this something interesting to everybody in this room?
Yes.
Okay. Just you, or?
No, I think it gives us limits on the encounter. So if you find a population of ultra-compact binaries, that tells you something about the number of interactions and the kind of interactions that those binaries have experienced, given the density of stars and black holes and all the rest that we think are in there. So yes, that's an important model constraint.
Okay.
Any other comments about this? Okay, so
A short comment about the binaries of black holes in the Galactic Center. So I just want to say about the paper appeared recently from my colleague Taras Panamaryov in MNRAS. He actually did a million body simulation of the Galactic Center with the black hole and tracing all binaries that dynamically formation and initially formed binaries. So probably this would be also interesting for you to look up onto the statistics of binaries. So black hole binaries, or whatever different binaries from black hole and main sequence stars with black holes, with neutron stars. So they have quite a nice statistics, and they still planning a new simulation also with a million body, so million stars in the Galactic Center. So probably that would be very interesting to see on the statistics.
Okay, thank you.
okay.
So actually, you also mentioned the CVs that you didn't see, right? You saw outside, but did you see any CVs in the center of the parsec?
We do see a lot of CVs inside one parsec. You see both of them, like magnetic CVs and then XRV. So it's not like, magnetic CV distribution is also peaked around the Sagittarius star, and it's basically following the nuclear star cluster profile, roughly speaking. So yes, there are lots of magnetic CVs too.
So that can be used as constrain the dynamics there, because the CVs, right? They originally started as a relatively wide binaries, like maybe more than one AU of that. Yeah. So in principle, and they are low mass. So in principle, they should have been evaporated. Well, depends where, but in principle, that can be used to constrain all these issues.
That's very interesting, because so you're talking about really like right around the Sagittarius star. So these wide binaries like magnetic CV may not exist. So maybe you expect some kind of hole, and then you start following the NSC outside. Oh, that's very interesting. So we'll look it up. Yep. Thank you.
Okay, so let's move on to another set of questions. I guess, or maybe
skip this.
skip this. Okay. So I think another interesting question is to ask how we can distinguish among different astrophysical merger channels. So there are several merger channels, as we've discussed. And so what types of observations or analysis would be needed from the theory side to compare to the observed distribution which LIGO can measure. So the observables for LIGO is basically the rate of mergers, but the problem is this is an absolute number which may be very difficult to calibrate. But maybe a simpler thing to do is just to predict the distribution of source parameters, which is a relative measure, with respect to different parameters. And just you should do this for all different types of channels and see which one match the observations the best. And of course, this was already discussed today by Fabio. And yeah, so here, for example, there are specific predictions for different eccentricities, spins, rates, and masses.
Could you sit down?
But we could, in principle, look for correlations between these parameters as well, right? So, for example, are the eccentric sources typically more massive or less massive, or how do these different distributions compare? Do you want to comment on this, Fabio, or?
Yeah, I mean, I'm not sure if I have an answer to your question. Yeah, so this is, yeah, I think it would be useful maybe if actually at the end of this workshop we had something like this for all the possible channels, black hole merger channels from galactic nuclei, apart from these two specific channels that I have discussed during my presentation. But so I think it would be useful, for example, to add to this the AGN channel. I don't know if we have already discussed whether we have predictions for the eccentricity distribution. Maybe yes, maybe not. Spins also are important, of course, and the correlation between spins and eccentricities. That in some, I'm not sure whether there is any correlation between these properties that I can comment on. There are other channels for which this is easier to do, but yeah.
Yeah, just a quick comment. Yeah, maybe we, as Fabio said, we could fill this out, but perhaps we're left with only writing what we need to do to learn these things. And I would add one more column, and that's the redshift distribution. For example, Carl has a recent paper looking at this for globular clusters, and I think that's also very useful.
Oh, no, I didn't have anything to say.
Another so redshift, but also localization, right? So I think that's going to be another tool to do this. And I think, so one of the difficulties will be, I think, differentiating between field binaries and all the other ones is going to be more straightforward. We don't need anything complicated. I think differentiating between the different dynamical mergers will be much harder, and that's where we probably will need multiple of these parameters to see in combination, essentially.
Okay, so yeah, just another thing I wanted to point out is just if we measure the eccentricity distribution, we can immediately have a robust estimate of the typical velocity in the host environment. So for example, so this is a paper we did with László Gondán, who's a graduate student. So we've looked at the gravitational wave capture scenario in the galactic nuclei, and in that case, it turns out that the peak of the eccentricity distribution at the less stable orbit correlates with the velocity dispersion of the host environment. And since the more massive objects segregate more deeply into the potential well of the supermassive black hole, they will end up being more eccentric. So this is how the distribution looks like. For the most massive component, it's at the less stable orbit, it peaks at a few tens of % or eccentricity, but for the lower mass components, which are further out in the galactic center, the distribution peaks at less than 10 to the minus 2. So this is another thing we should look at. And the measurement error of the eccentricity at the last stable orbit is between 10 to the minus 1 to 10 to the minus 4, depending on what the actual value of the eccentricity is. So for more highly eccentric objects, it's very easy to measure the eccentricity very accurately, but for low eccentricity objects, it's difficult. And in the case of globular clusters, the more eccentric sources basically correspond to binaries which have high velocities to begin with, right? So if you have this resonance scattering of 3 objects, so you have a binary and there's a third object coming in, or even a binary scattering. If you have an immediate merger of another black hole, the eccentricity will be higher if the original velocity of the binary was high. If the original binary velocity was low, then the eccentricity will be lower, right? So even I think for binaries, you would learn something, I mean, for globular clusters, you would learn from the eccentricity distribution something about the original binary population. Is that?
I mean, after our last conversation, I actually looked at this, and I was not able to find any correlation. I think it's because you basically will continue hardening the binary until its energy, independent of mass, or its energy, which depends on the mass, is roughly, beyond the escape speed, or rather the recoil that you get from it. I don't think it depends so much on the velocity. Basically, there was no correlation as far as I can tell. I think that only really works for the cusp scenario.
Surprising.
I could just have not enough statistics. That's also possible.
Okay, another thing which we could look at in principle is just the mass distribution. So the interesting thing is if you have two, so you're basically measuring 2 mass parameters with LIGO, and you could basically measure the relative rate of mergers for different component masses. And the thing is, you don't know what the black hole mass function is. This is an unknown function, f. And so you can assume that, let's say, in a globular cluster, you randomly draw an element from this black hole mass function and another element, but the merger rate could depend on this conditional probability of merger, which is also unknown. But the question is, if you measure this R, can you independently infer L and F?
What is L again?
So L is the conditional merger probability for a fixed 2 masses. So how much more likely is it to merge a given binary with some M1 and 2 compared to the random pairing probability? And it turns out it's really interesting. So I asked this question in an email from these co-authors, and they immediately responded that this is simple. This is what you need to basically measure. Just take the logarithm of the rates and this mixed derivative, and if you look at it, of course, you can see that the logarithm of a product is just the sum of the logarithms, and if you take the mixed derivatives, the black hole mass function just drops out. So this will not be sensitive to the black hole mass function, but only this merger probability, which can be predicted for different types of channels. And this turns out to be something like 4 in globular clusters, although this has to be checked again. So this is just based on a paper we did in 2016. But you can calculate this very accurately for the gravitational wave capture scenario, and this turns out to be 1.4 in collisionless system, and it changes between 1.4 to -5 in galactic nuclei, and it turns out to be 1 for the primordial black hole channel if the binaries are formed in the early universe. So this is another thing that you can in principle check. Just measure this number and see which one.
If you randomly pick the masses, this would be 0, right?
If you randomly pick, yeah, then it would be 0.
Okay, just make it sure I understand.
What is it for field binaries? For field binaries?
So that's the thing that it needs to be checked. So I'm presenting this as something to do for the future. I think all of the channels should just theoretically predict this number and see what it is, compared to observations. And finally, I wanted to just highlight some smoking gun signatures. So what types of observations should we get to immediately know where the source is coming from? So one idea is just this Doppler shift. So if you have a binary orbiting around a supermassive black hole, you can, if you measure the Doppler shift, you can immediately say, like, what is the orbital period of this object around the supermassive black hole, and basically confirm this source. So this is one idea, and with LISA it will be much more easy. So for these types of sources which start from the LISA band and end up in the LIGO band much later, it will be much easier to do these types of measurements because you just have more time for the orbit. So this is one thing. The other is this quasi-Lydev oscillations. So there were these two papers last week on the archive. One of it was by Baomin Huang and Smolanaus, which showed that in the LISA band you can have these sources, these eccentric sources, which move in eccentricity on observable timescales. So what?
We've been talking about doing this for a while, and then y'all beat us to it. Sorry.
Okay, so yeah, so in principle you could just see a source move in eccentricity back and forth, and from that you can infer the triple companion properties. For example, if it's a supermassive black hole, and so if you have a binary around a supermassive black hole, and so in this case it's very optimistic. The top panel assumes a source in our own galaxy. But even if you go out to 1 megaparsec, it turns out that you can statistically significantly measure the difference between two waveforms with and without the perturber. So you can basically, even at 1 megaparsecs, measure the effect of the perturber. So, and finally, the gravitational wave echo is another idea. So what you can look for is this lensed image, even if it's not strong lensing. So if it's strong lensing, then the lens signal could be, the secondary signal could be stronger than the signal in the absence of this lens. But in typical cases, if the deflection angle is larger, the secondary gravitational wave will be fainter. So it will be difficult to detect this, but if you do, then you can confirm that, okay, this source happened near a supermassive black hole. And you only have a realistic chance to do this within, say, 100 or 1,000 Schwarzschild radii of the supermassive black hole. If you're further out, it will be really, really unlikely to have this. But I was just wondering if anyone else has any ideas for these signatures.
No, I'm just going to jump off this. Doesn't this mean that all of the LIGO black holes could actually secretly be 10 solar mass black holes merging at redshift 2, and they're just being lensed by the supermassive black hole in front of them?
So we looked into this, and it's very unlikely because, well, if all of them were so close to the supermassive black hole, then yes. But otherwise, it will be, I don't know. So yeah, so that's a good point. But you could look for the other types of signatures in that case. If you're so close to a supermassive black hole, it may change the properties of the signal. Not for LIGO, but.
But isn't that where the resonance traps are anyway? I thought they were like 25 and 3. Isn't that where the resonance traps are anyway? I thought they were all like 25 and 300 gravitational radii.
Schwarzschild radii.
Oh.
Yeah, Schwarzschild. So they're like, it depends on the map. Yeah. So yeah, they're about 600, gravitational radii, but yeah, 300 Schwarzschild. Yeah. Yeah. This is.
Well, I think I was going to bring this up on Wednesday when we talked about EM or whatever observables, but just going on, since we're talking about it now, then aren't the orbital periods, depending on the mass, but for, normal supermassive black holes, small enough to watch not only, just one epoch of lensing or Doppler shift, but to see it change over the orbits, to see the acceleration, and then you can do a lot more. So, I mean, I don't know if that's already in here, but you can see the magnification change in this, yeah.
I was just going to ask on the previous one, are you saying that if the merging binary is 1 megaparsec away from a perturber? No.
It's from us. The source distance is.
Oh, the source distance is only 1 megaparsec. Oh.
The perturber is just next. It's the supermassive black hole in the.
Right. Okay. That makes much more sense. Okay. Yeah. Oh, but so then 1 megaparsec away, we're really talking local group.
Yes.
Okay.
For that one.
Yes. So can you describe the upper right panel again? So
this panel?
It's one source.
Yeah. So we have a source in the LISA band. So the problem with LISA and eccentric sources is that you have rarely this weak burst of gravitational waves, and it's faint. It's weak. So that's why you're restricted basically to the local group. But if you're lucky enough to find such a source, so you have a binary orbiting around each other in the LISA band, then since the source is eccentric, if you cut the signal into 1 month duration segments, then this is what the signal gravitational wave spectrum will look like for different time segments, so different months. So first it will look like this, and then it will gradually increase its eccentricity as the supermassive black hole excites the eccentricity of the binary, and then decrease it back. So this is still in the quasi-Lidov regime. It's not the gravitational wave driven regime yet. That comes later.
We're very close to the wine reception, so we should keep our comments very brief. But one final thing, I think. Ongoing LIGO searches for bursts, I think, are very useful because they constrain. So there are several instances that we've already discussed where highly eccentric binaries can be generated. So ongoing limits on bursts from Bremsstrahlung from those highly eccentric encounters is very useful. So that's an additional constraint that we can throw into the mix that will help us. Right.
I would also say that there's probably one other, maybe a smoking gun for the AGN scenario, is if you have a pretty high mass ratio encounter with a pretty large total mass. So by that I mean if you have a 10 and a 100, or a 500 or something like that at the top end, I think we're the only scenario that comes up with a merger that looks like that. Okay. So that's.
Sorry, what was it again?
If you've got like a 10 and 100, so a high mass ratio with a large top mass. So basically, because in the AGN scenario you get so many bites at the apple, it's hard to eject them even with a substantial kick because they're sitting in a really deep potential well. And so if you build up an intermediate mass black hole, but there's still some stellar mass black holes being driven in from the outermost regions, you could still have a 10 sort of arrive at a migration trap in some rational length of time and then hit that 100 or 500 solar mass black hole, and then I don't think anybody else has a scenario where that happens.
Can you put again the different ideas for merger there? So we had the AGN and the globular cluster, right? The isolated evolution. I was wondering about that. So I was talking to Carl actually about that. What are the cons of that? Because apparently you can't do that, right? With top 3 stars, right? They can be massive enough to collapse, right, into hefty black holes. So I was wondering then how we can, well, like what would the the cons of this model be?
Do you mean just like why would we disfavor the standard binary style evolution picture?
I mean, what are the observables, right, that are listed there that could rule it out?
So I mean, Richard's in the room, so I could I'll try to do my best. But I mean, part of the problem with this with isolated binary evolution is that because we understand the mass transfer phase so poorly rather, it's really easy to tune a lot of that to reproduce anything. So for instance, common envelope could produce all of the binary black holes we're seeing or virtually none of them. And there's not really a good way right now to distinguish the two. For a while, we had this idea that, yeah, the spins from the common envelope channel would be aligned. They can get somewhat misaligned by supernova torques. You can imagine that maybe massive stars start off with misaligned spins. Unfortunately, LIGO is just giving us everything with zero spin, so that kind of becomes boring. The other part of the reason I've been focusing on a lot of things that dynamics gives you and not common envelope evolution is because the dynamical channels tend to produce things that are a little more exotic, like these very high mass ratio objects or very high eccentricities, both of which are very hard to get from isolated binary evolution. I think the only way you could potentially rule out any of the binary stellar evolution models would be if they all predicted very high, very aligned spins. In that case, I would say it's been ruled out, but that's not necessarily required. And even then, if you believe the IAS's recent results, we actually now have a binary black hole with very high aligned spins. So, do you want to add anything, Richard? Or
I think that's pretty fair.
Can we ask Richard to close it with a dance?
Maybe the prayer session.
I'm going to eat.